Hello everyone, my name is Kushal Agarwal and I'm a student here at IIT Roorkee in Data Science and AI branch, and I am here to present my C++ project on the topic of encryption decryption system. I have named the system ExCrypt. Now let us discuss about ExCrypt. Now first we need to get an overview of what we are going to discuss in this video. So firstly we will be starting with the basics and knowing what exactly is encryption, how encryption is used in nowadays world, and why it is relevant in today's digital era. When there is so much of digital footprint, there is so much of digital data, there is so much of stored data in the databases, in the cloud storages. So why encryption decryption is important and how it ensures your data is protected online, and how your personal information is protected from being exploited. Okay. After that, we will be knowing some common and some advanced encryption decryption techniques and mechanisms that are used nowadays to protect your data online. We would be discussing what exactly mathematics and what exact algorithms they are using on the back end, so that they protect your data from getting exploited. After that, we will be knowing what our ExCrypt system is, what techniques our ExCrypt system is using, and then we will be deep diving into those techniques and knowing what exactly those algorithms do. If we think that those algorithms are purely coding based, so you would be wrong. Those algorithms are purely mathematics based, and we will be knowing that mathematics. We would be deep diving into the spreadsheet algorithm. We would be deep diving into the binary operations that it is using. We would be knowing how what matrices operation they are performing, how it is arranging the bits and bytes of your information into the spreadsheet, and how they are superpositioning them so that it generates a ciphertext at the end. We would be looking into that. After that, we would be deep diving into the code part of the system, and we would be knowing what exactly libraries we are using in the system. Especially we would emphasize on the OpenSSL library used in the system and why it is important to sustain the ExCrypt system. We would be looking into many different libraries and all the functions and algorithms that those libraries bring into the system to maintain the workflow of the ExCrypt system. Okay, after that we would be looking into the class structure and the modular structure of the ExCrypt system, and we would be knowing what exactly each and every class is doing and how it is contributing into the workflow of the system. After that, we would be looking into the line by line code of the system, and we would be knowing how each line of code and function is contributing and maintaining the workflow of the system, and maintaining the workflow of the system in which a file can be encrypted and decrypted. The important key and passwords are stored in the header, and then those key and password are used during the decryption process. Okay, so after that we would be looking into what are exactly some of the flaws that are present in this encrypt system, and how those flaws could be enhanced so that this system could be improved into such a system that could be used in real world applications, and could be used to protect your data in today's digital era on the internet, from being exploited from real hackers and exploiters. Okay. Even though the ExCrypt system is using many advanced techniques like XOR and AES CSM, which is an international encryption standard, and it has very strong mechanism. Still the system have many weak points and vulnerabilities that could be exploited by real hackers. So we need to address them and know how we can enhance those capabilities, so that to make the system very strong and cryptographically impossible to be broken down. Okay, so now let us begin with the video. Okay, first of all, we would be understanding what exactly is encryption. When we talk to people what exactly encryption is, so they think that encryption is some kind of technique to protect their data online through some code, or getting putting some lock on their data. But exactly when we talk about encryption at code, it is basically applying many type of operations on your plain text to convert it into ciphertext, so that so that your plain text becomes unreadable to the hackers and exploiters. The hackers and exploiters cannot read your data. People think that encryption protects your data from getting breached, so that if you have encrypted your data, the hackers and exploiters cannot get your data. But that's not the case, because when you encrypt your data, it does not ensure that your data will not get breached, your hacker will not get access to your personal information. Instead, ensures that if the hacker gets the access to your personal information, he is unable to read it or reverse it into a plain format, so that it could be implemented into the system, so that he could exploit your identity or financial details or banking sites to gain access to your personal information. Okay, so exactly, encryption ensures that your data is secure in such a way that the hackers are unable to read it, and it makes your data cryptographically strong, in spite being vulnerable enough to get breached into their system. Okay, now exactly what is the importance of encryption? As we have discussed, it protects your identities and helps in case of data breaches. So it is very important to know in detail what exactly happens there. So let us take an example. If if you are sending an email to a person B, that email travels through many nodes, many routers, many other routers, many other choke points, where this mail can be intercepted and could be read and exploited or tampered. So what happens is that if this mail is unencrypted and is sent like this only on the network line, so what will happen that any hacker or any exploiter in between can tamper and read your personal information that you have written in that mail. So we do not want that. So what we will do is that we will encrypt this mail using some advanced mathematics and change it into such binary text, so that the hacker or the exploiter is unable to read that. If the hacker and exploiter would read it, he would just see bunch of symbols, bunch of binary text, which is nearly impossible to be read, and it is also cryptographically strong enough to reverse them into other plain text. If we have sent it over the network in encrypted format, the hacker would be unable to read your information and steal your personal information, personal identity on the internet. Okay. Now, when we talk about secure transactions and banking infrastructure, it is very important. The encryption decryption system is very important. Now, let us assume that there is a company who has terabytes of data of millions of people. Let us assume a banking company who is having a database which is storing the person's pins, password, their credit card, debit card information, and many other personal information. We do not want that this information to get breached or get leaked into hand of people who have bad intention and want to exploit the other people's identity and their financial assets. So, what these companies do, they encrypt their database, and it is very important to encrypt their databases, because if this database is not encrypted, means one part of in this cybersecurity field is that to protect that data from getting breached. That is the primary aspect. So the companies do not want that data to get breached into the hand of the hacker. But in case if that data gets breached, so it is very important to ensure that those hackers are unable to get the access to the personal information. They are unable to read the password. They are unable to read the pins of the people. They If the person knows also that this is the password of any person, he is unable to know what exactly is the customer ID or the pin or the name associated with that pin and password, so that it is unusable, and it cannot be used to exploit the financial assets of the person. So the complete banking and the financial infrastructure stands on this encryption decryption process, and it is very important to ensure that encryption decryption is extensively used in this. And when we talk about our digital footprint and our digital data that we have on the internet, like many of our videos, images, text, hundreds and thousands of texts, images, and some personal information shared over the internet, social media websites, messaging apps, mails, Twitter, etc., and many other sites which we use in daily life. So we want that all these data should not go into hands of someone who can exploit it and use it as your identity to take a loan, or maybe act as you online and defame your character, or many other things could be happen in case of your identity set. So we want that all this data is to be protected. So there are all these companies, all these social media websites, all these messaging websites, mailing websites, all these use different decryption systems, and they ensure that your personal information and your personal data and messages are encrypted and are unreadable to any hacker who is reading them, and he or she is unable to know what exactly you are messaging to other people, or other people on the internet, and which maintains your integrity, confidentiality, and character over the internet. Now, it is very important to know what exactly are the applications of encryption decryption. So, as we have discussed, messaging apps, cloud storage, banking system, and the financial system have extensive use of these systems. Now, when we talk about messaging applications, so let us assume an example of WhatsApp. When you are messaging on WhatsApp, you have always seen above the message when you are typing, there's always a block of text written that this message is end-to-end encrypted, and your personal messages are safe to travel over this network. So what happens is that WhatsApp uses an end-to-end system in which the source as well as the destination messages as well as their network IPs are encrypted enough so that a person who is intruding this network line in between cannot know from where the message is coming, from where the to where the message is going, and what exactly is the message. So this is the system of end-to-end encryption, which is extensively used in the social media websites, messaging apps, and other storages. Okay, now when we talk about cloud storages, so we know that there are many companies which manage a lot of cloud and internet data, like Amazon, Google, and many others. They have uh, thousands of terabytes of storage, which contain many personal information as well as confidential information, which is very dangerous to get breached or leaked into the to the common public. So these cloud storage companies use very advanced encryption systems, so that even if their data gets breached, the hackers or the exploiters are unable to read the data and exploit them into their favor, and cause any damage to the person's identity, to any governmental data, or any other financial assets in the world. And we have looked into how these encryption decryption systems ensure that the banking system and the financial infrastructure stands on its leg properly and functions smoothly. So now let us move further and know what are some common encryption, decryption, and hashing techniques. Now, some of the encryption decryption techniques could be broadly separated into two types: symmetric and asymmetric. So now, what are symmetric techniques? Symmetric encryption techniques are those techniques which uses the same password or key at the source of encryption and at the destination where the message is to be reached. It means that if you have used a password named key at the source to encrypt the file, so that same password, which is key, is used at the destination also to decrypt that encrypted file into the plain text. So this is the symmetric type of encryption. And in asymmetric type, exactly as you think that uh, a private key is used at the source of encryption, which converts the plain text into encrypted text, and then at the destination a public key is used to decrypt that encrypted file into decrypted and original plain text, so that the destination person could look into the plain text of the plain text of the file and know what exactly is written into it. Now, let us talk about some of the techniques like mentioned here. XOR and AES. XOR is basically the XOR technique based on the XOR binary operation, which we would be looking into, and the AES, which is the Advanced Encryption Standard, which is the international encryption standard used used nowadays to encrypt the systems and files or data over the internet. These both techniques, are techniques. These are symmetric encryption techniques used nowadays. They are very strong in algorithmic wise, but they lack a very key role of determinism, because they always generate because it is very important whenever we are using the same key at the source and destination. So it is very important to transfer the key over the network also, so that key can also be transmitted or intercepted in between, and can be used to decrypt that encrypted file which is being transferred over the network in between. So it is very important in these symmetric techniques that the transfer of key over the network is secured, and should be secure enough so that it could not be intercepted in between, and the file cannot be exploited in between by any hacker or exploiter. Now, when we talk about some asymmetric techniques, RSA and blowfish are the ones. When we talk about RSA and blowfish, these are asymmetric techniques. Whenever on the source we are trying to encrypt the file, we use a private key which is generated by us, and this private key is used to decrypt the system. Then used to encrypt this plain text into an encrypted file. After this private key is changed into a public key and stored inside the header of that file, and then this file is transferred over the network. So in this way the private key does not get exposed, as well as the public key, which is always public and is accessible to everyone, can be used to decrypt that file. But it is very important to use the component of private key as the destination to decrypt this file, which lacks in the public key. So this makes the system very secure, and at the destination the person can open the file without any tension of the key getting intercepted in between, and any tampering of the file and data in between of the network. Now, a very another very common thing used in the encryption decryption mechanisms is the hashing. The hashing process is very important in the system, and some of the common hashing techniques which are used nowadays is SHA-256, means the SHA class, which is the secure hashing algorithms. It is a class of hashing. It is a class of hashing algorithms, and SHA-256 is one of the algorithm in between, which is a symmetric hashing algorithm, and Decrypt is a unsymmetric hashing algorithm. So now let us move forward, and firstly it is very important to know that what exactly is the difference between encryption, decryption, and hashing. First we will talk about what exactly is hashing. So hashing is a one-way process of changing your data into a ciphertext. When we talk about encryption decryption, so it is bidirectional. If you have encrypted any data, so it is a so we are able to use that same mechanism to decrypt that data into a plain text again. But this is not the case with hashing. Hashing uses much more complex mathematics and much more complex operations to change the plain text into a such kind of ciphertext, which is almost impossible to get reversed to get the plain text. Hashing is a very strong technique, and it is only used single directionally. It is generally used for passwords and passwords to generate key, which these keys are further used in the encryption decryption system. Because when we put any key into these systems encryption decryption mechanisms directly, so as we know that people use very deterministic key, some people like many people, a very common password is 123456. So this is a very common password, and hackers also know this, so they would directly try to use some common passwords into this encryption decryption systems, and are many times able to achieve it also, and are able to decrypt these files without even knowing the password, just by guessing them from the commonly used password. So it is very important that these passwords are first changed into a key that is undeterministic. So these hashing techniques come here, and these change these passwords into undeterministic keys, which are then used into the encryption decryption system to encrypt these files. Okay, so now some properties of hashing is that when we talk about encryption decryption, so if you have put a file, let's say, which is about 1 MB in the encryption mechanism, so it would return you a encrypted file of 1 MB, and it would return a decrypted file of 1 MB. But it is not the case in hashing, because if you have entered a input of 10 bits, let us assume, then also the hashing techniques would return you an output of 32 bytes. If you have if you have entered an input of 1 gigabyte, if you assume, so then also these hashing techniques would return you the output of 32 bytes. So the output size and length is always fixed in these hashing techniques, and it always returns a fixed length of output. Another very big characteristic of these hashing techniques is that they are very volatile. Like, let us assume that if you are writing 123456 as your password, and this thing is hashed into a 32 byte into a 32 byte key. So if you just change even the slightest into this password, if you have written it as 123457, so this would completely transform the hash or the key. If we say that only the 6 is being converted into 7, so a small change should occur into the hashed key in the output. So this is not the case. The hashed key completely converts each and every bit of the hash key gets converted into some other output that is you that comes out after applying all of its mathematics, which we are going to discuss further in this video. Okay, so now when we know a clear distinction between encryption and hashing, now let us move forward and know what exactly our ExCrypt system is doing, what exactly is the workflow of the ExCrypt system to pull off this whole process of encryption decryption. So first of all, the ExCrypt system would ask you that what exactly is the operation that you want to do. It would ask that do you want to do encryption or decryption. After that, it would demand you to tell which mechanism you want to use. So basically, I will tell you that the ExCrypt system is using mainly three mechanisms. For hashing process, for hashing process, our ExCrypt system is using SHA-256 mechanism, which is a very secure and highly mechanized system, which is nowadays international norm used in the encryption decryption system, and a basic requirement for the companies and the hashing algorithms to use this kind of security system. Okay, for encryption techniques, we are using basically two techniques: XOR mechanism, which is fast, less reliable, less secure, yet very fast, which is used in less confidential or vague messages over the internet. The messages which are not that very important, but require a large amount, require a very high speed of encryption to be transferred very fast over the internet. Okay, the second mechanism which we are using, encryption mechanism that which we are using, is AES 256 GCM. Okay, it is basically the international standard which are used nowadays by many companies like Google, Amazon, Microsoft, etc. Many different companies uses this AES 256 GSM mechanism is because it is a very strong mechanism. It consists of many characteristics which we will be discussing ahead. It uses many advanced mathematic operations to pull off its encryption system, and it attempts those system in multiple rounds, which makes the system very secure, and makes and it also ensures the authenticity of the password. When we talk about this AES, the AES 256, so AES 256 is basically the encryption part in the mechanism. And GCM is basically the name of the authentication mechanism used in the AES 256 GCM technique. So GCM ensures that your data is not tampered or not changed during the network propagation, or is not tampered in between, so that it checks each and every bit from the original bit, and checks that if there is any change in between, it do not decrypts the file and remain it as encrypted file. So to avoid any kind of virus or any kind of damage which could happen to your system due to that file tampering. Okay, so now let us see what exactly happens into our encryption system. So first of all, we would tell that what encryption decryption function we have to do, what mechanism we are going to use. Then the system would demand you to tell the path of the file and tell the output path of the file. That where you want to input the file and where the output would come. Okay, so after that, you will set a password for the file, so that password will get hashed using the SHA-256, and then this would return a 32 byte key. This 32 byte key would be used into the encryption process, as you have decided. If you have chosen XOR or 256 ES256, so the system would choose that mechanism and put that 32 byte key into that, use the file path, and then encrypt the file and return it and store it into an encrypted folder. Okay, so this file is stored into a safe storage, which is also encrypted, which is named as encrypted file. So now let us check that what is the decryption workflow of this ExCrypt system. So when we get the encrypted file into a folder. Now, what if we want to decrypt that? So this file is then decrypted in the following process. First of all, we will tell the name of the file which we want to decrypt. Then we will choose the mechanism from which we have encrypted that file. Then the same process would be reversed. We will enter the password. That password would be hashed with SHA-256. That password would be matched from the original key stored inside the file, uh, file tag, file header and tag, that would maintain the authenticity of the file. Okay, so after that, we will use that mechanism of XOR or AES-256 to reverse the process, using the 32 byte key, and this would return output decrypted file into a yet encrypted folder, which is named as decrypted files. So this was the overall workflow of the ExCrypt system. And now we will deep dive into further. We will deep dive into the system, and we will know what exactly is the mathematics which is used behind the techniques used in the system. Basically, we are talking about three techniques used in our system: SHA-256 XOR encryption mechanism and AES-256 GCM encryption mechanism. So we will looking into that and know what exactly is the mathematics, what exactly are the operations, what exactly are the each and every bit byte transformation and superposition used in these techniques to convert your normal looking text into a text which is unreadable or cryptographically so strong that the hackers or the exploiters are unable to approach it and use it in their favor. First, we will be talking about SHA-256. So basically, in SHA-256, first of all, a very important process is padding. Okay, so the padding is the first step of SHA-256. After padding, the password, your password is converted into blocks of 32 bytes, and those blocks are then further goes into many matrix operations, which further goes into more than 1 lakh rounds of continuous hashing and continuous mathematical operations, which is then converted into many 32 bytes block, which are then XORed and concatenated to create a single 32 byte block, which is your hashed password and key. Okay, so now let us look how exactly the mathematics work. Okay, so first of all, we will look what exactly are some of the basic operations. Let us start from the scratch and what understand some of the basic operations. Okay, so few basic operations that we need to understand is first of all the not operator. Okay, so the not is a binary operator whose truth table is that it converts a zero bit into a bit one and a bit one into a bit zero. So basically, it turns an off bit into on bit and on bit into off bit. Okay, so this is our not operator. Then we will be going to understand what exactly is the or binary operator. Okay, so the truth table for the or binary operator, it is a binary operator. So it would take two inputs, which is A and B. So if both the inputs are zero, so the or answer of this would be zero. If they are zero and one, if they are 0 and 1, so the answer would be 1. If they are 1 0, then also 1, and if they are 1 1, then also 1. Okay, so this is basically the truth table of the or operator. After that, we will be going to understand what exactly is the and binary operator. Okay, and binary operator. So here also we will understand the truth table of the and binary operator, and it also takes two inputs, and the and answer of this. Okay, so basically, in the AND binary operator, what happens is that if both the inputs are zero, so the output is zero. If one of the input is one and the other is zero, then also the answer is zero. And only if both the inputs are one, then only the output answer is one. So basically, and only returns a turned up or a positive value only when the both the inputs are turned on. Okay, so using all these basic and elementary binary operations, we create some complex binary operations which we have to use extensively in our system. So first we will discuss about the XOR operation. So basically, what exactly is the XOR operation? XOR operation is also a binary operation. Let us assume there are two bits, A and B. So what exactly the XOR operation is used for? XOR operation is applied on this bit, and the mathematical operation that XOR uh, carries out is uh, carries out is this. Okay, so okay, This is the mathematical operation of the XOR operation. Basically, this dot is used to represent the OR operator, and this plus sign is used to represent the AND operator. And the small dash above the A and B is basically representing the NOT operator. This XOR operator is basically a mix of OR, AND, and NOT operator. And let us now see what is the truth table of the XOR operation. So XOR operation takes A and B as input, and basically, XOR operation returns a turned up value whenever both the inputs are different, and a off value when both the inputs are same. Okay, so if both the inputs are zero, the answer would be zero. If both the inputs are one, the answer would be zero. And if the inputs is zero one, if the inputs are zero one, uh, inputs are zero one, and inputs are zero one or 1 0, then the answer would be 1. So it is turned on when both the inputs are different, and turned off when both the inputs are same. So basically, now we have understood all the basic binary operations, and now we will look into what exact operations are used inside the SHA-256 mechanism. Okay, so first of all, we will understand the method of padding. Okay, so what happens is that let us assume that your password is of only 10 bits, but we want that your password is converted into a 256-bit block, because we in SHA-256 we deal these mechanisms and all these mathematicals and matrices operations on the 256-bit matrix or block. Okay, so what happens is that let us assume that you have a password which contains 10 bits. Okay, let us assume something 100 something 101. Okay, this is your 10 bit password. So what would happen is that we will add 256 what will happen, we will add 246 zeros in front of your password, so that this whole gets converted into 256 bit of password. Okay, so this get converted into 256 bit 256 password. Now what happens is that after a 256 bit of password has been formed, so it is arranged into a matrix or a block, we can say. So what happens in this block is that there are total 32 rows in this column, 32 rows in this matrix, and 8 columns in this matrix. So each byte of our each byte is arranged uh, in such a way, and each of the 32 bytes of this password is arranged in the rows of this matrix. Okay, so now this is the case when your password is below the 32 below the 32 byte below the 32 byte criteria. Okay, what if your password is more than 256 bits? So let us assume that your password is 400 bits. Okay, your password is 400 bits. So what would happen is that now we will deal with the multiples of 256. So the next multiple of 256 is 512. So what would happen first, so the last 256 bits of your password, the last 256 bits of your password would be converted into a particular block, and the rest left number of bits, which are exactly 144 bits, would be then converted into the next block. In the next block, by completing the padding process. Okay, so what would happen is that in 400 bits we will have one pure password block and one padded block. Okay, and after that these multiple blocks of 256 bits are formed. What would happen, we will XOR each block. So what would happen, while XORing each block, each cell of the first bit will be XORed with the second bit, second with the second cell, third with the third cell, and so on. All the 256 bits would be XORed with each other, and the result would be a final 256 bit block. Okay, then the mathematical operations would be applied on this 256 bit block. Okay, so now before moving further into the mathematics and the matrices operation applied on this 32 byte block, we will see what are some symbols that are used in the in these mathematical operations. So basically, a plus covered with a circle is used to represent the XOR operation. Okay, this sign is used to represent the AND operator. Okay, if a dash is put above any bit, so that is used to represent the NOT operator, and so on. Okay, we will discuss if any other symbol is encountered in between. Okay, so now let us talk what matrices operations are applied on this. Okay, so first matrix operation is ROTR, which stands for rotation mechanism. Okay, so what happens is that we know that we are having a matrix which is 8 by 32. Okay, this is 8 by 32 matrix, and what happens is that there are rows and columns in this matrix. Okay, so what would happen is that we will take x number of basically ROTR, rotation is a column transformation operation. So what would happen is that we will take x columns from the start, and we will shift those x columns at the end of the matrix. So let us assume that if we take the value of x as 2, so the first and second column of the matrix would be shifted to the last two positions, and the third and fourth column would be shifted to the first and second position, and so on. The whole matrix would be rotated. Okay, now, what happens when we put a power n on this ROTR function? Okay, so what happens is that if we start with a 32-bit block, which is 32-bit block, which is a 8 by 32. Okay, so what happens is that let us assume we are operating it with ROTR we are operating it with power 3 ROTR power 3 and base 2. Okay, so what would happen here is that first to for this function, what would happen for this matrix is that the first two columns of this matrices would be shifted to the last position. After that, the third and fourth column would reach the first position, and then again the same operation would occur, and this operation would occur three times. Okay, so this 32-bit block would be converted into a completely new 32-bit block. Let us say that that block is B, which would be formed after rotating this matrix three times by two columns. Okay, so this is the ROTR function, and now we will discuss the next operating function used inside our SHA-256, which is the SHT function. So basically, SHTX is a row operation function. So we know that we are having a matrix which is 8 by 32. Okay, which is 8 by 32, and we need to operate on it. Okay, so what happens in SHTX operation is that basically it is the rotation function only, but it is for the rows of the system. So we will take x rows from the starting, and shift them to the last of the matrices. And similar to the ROTR function, if we raise it to a power of n, so this operation would be performed n times, again and again and again, and matrix A would be converted into matrix B. Okay, in this way. So we will get a completely transformed matrix after the ROTR and the SHT function. Okay, so these are the basic operations. Not these are not the actual operations that are used in the SHA-256 function. These are the sub functions. We will know how these ROTR functions, all these binary functions, these SHT functions are used together, so that to create some functions that are complex and could create a very cryptographically strong mechanism. Okay, so now let us understand what are the main functions that are exactly used inside the system, used inside this SHA-256 system. So the first operation is the big signum function. Okay, the big signum function is represented by this symbol. What exactly is this big signum function is it is consists of multiple ROTR functions used simultaneously. Okay, so what happens is that ROTR function, basically the mathematical equation of this big signum function is ROTR x power 1 plus ROTR uh, power 3x something 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 to ROTR power 31x. Okay, so power 31x. So this big signum function converts the basically one more error I have made, that this is not the plus symbol, not the concatenation symbol, it is the XOR symbol. So what happens is that a block is taken and this block is converted into the this 32 byte block is then converted by the ROTR 1 power 1 base x function. So it creates a matrix B. Then it formulates a ROTR power 3x. It formulates ROTR power 5, and similarly till ROTR power 31x. Okay, so all these blocks which are formed after these ROTR functions are then XORed to create a single final 8 by 32 32 bytes of block, which is then further used for further mathematical operations. Okay, so after this big signum function is used, we use a small signum function. So what exactly is small signum function? This is the symbol of the small signum function, and small signum function is basically a compilation of many SHT functions. So what happens in the small signum function is the mathematical equation of a small signum function is SHT power 2x XOR with SHT power SHT power 4x, SHT power 4x, SHT power 4x, XORing till SHT power 32x. Okay, we will XOR it till SHT power 32x is reached. Okay, okay. So after all these operations, this would return a x. We know that SHT power 2x would create a block that would be a 256-bit block, and this block would be this block is then XORed with the SHT4x block, then with the SHT6x block, and with many different blocks after this again and again and again. Okay, so what would happen in that is this again and again block XORing is done, and it would finally create an X matrix of 256 blocks in which all of these SST functions are applied. So this is basically the operation of small signal function. Now, for the next operation in the SHA256, this is called as the choice operation. The choice operation is represented by CH, and this operation is a special operation which is applied only on the 3 bits of this matrix. Okay, let us assume the mass XYZ. Okay, so what happens here is that when we take our matrix, okay, so basically the choice functionality is our row functionality. Okay, so what happens is that let us assume that there are these are the rows and columns of our matrix of our 256-bit matrix, and what happens here is that we will take 3 bits from this matrix. Okay, let us in the row direction. So this is x, this is y, and this is z. Okay, so we take these 3 operations, and what exactly is the mathematical equation of this this choice operation? It is basically x and operator is y XORed with not of x, XORed with not of x, ANDing with z. Okay, so this is the mathematical equation of the choice operation. So what happens here is that basically this is the mathematical equation, and in a vague way, if we try to understand, what happens is that the x is replaced by y. X is replaced by y if x is equal to 0. Okay, and x is replaced by z x is replaced by z if x is equal to 1. This is basically the operation that it is performing when x is equal to y. So x is replaced with y and z on the basis of the value of x. So in this way, these three bytes are purely hashed, and they are mathematically operated so that they become jumbled, and a completely new set of row is converted is formed. Okay, so what happens is that the first three cells are operated with this choice function, then the other three cells, then the other three cells, and till the complete row has been operated with the this choice operation. So what happens is first the 1 2 3 cell is operated, then the 2 3 4 cell, then the 3 4 5 cell, and similarly till the whole row is completed. And after a single row is completed, this operation is applied on each and every row, so that each and every byte inside the rows are completely jumbled and mixed up, so that it cannot be guessed or cannot be found by any exploiter or any hacker. Okay, so the next function we are going to talk about is the majority function. Okay, the majority function is represented by x. It is also an operation that is applied on 3 bits. Basically, it is an operation which is applied on the column direction. So what happens here is that, let us assume this is our matrix. Okay, so if we take three cells, this is x, this is y, and this is z. So what exactly is the mathematical equation that we are applying here is that x and of y XORed with x and of z XORed with y and of z. This is basically the mathematical operation that we are going to perform here. So what exactly this equation is telling us in a vague language, we can say that replace x with 1 and 0 according to the following condition. If at least two of the three x y z are 1, so replace the x with 1, and if this condition is not satisfied, replace the x with 0. Okay, so this is the condition that we need to follow here. So we have to replace x is equal to 0 if the xyz if the xyz is not at least two of them are 1. Okay, and x is equal to 1 if at least two of the three are 1. Okay, so this jumbles up the bits and bytes in a complete in the row wise, in the row direction. And how this majority function is applied, similar to the choice function. First it is applied to first three cells, then to the next three cells, then to the next three cells, and so on till the complete column is completed. First the one column is completed, then this function is applied to all the columns in the matrix, so that the column wise bits and bytes are completely jumbled and becomes random inside a becomes randomized inside this complete matrix. Okay, so now let us talk about what exactly happens in one round of the SHA-256. So now when we talk about the round of SHA-256, what happens is that firstly, through the padding process, we will get a 32 byte block. Okay, then that block would be first, we will get a block. Then this block is operated with the small signal function. Okay, small signal function, so that its rows would get jumbled up, rows get jumbled up. Okay, we will then get a jumbled up block. Okay, then this block is operated with majority function. Okay, then the majority function is used so that the bits and byte within the column are jumbled up so that it cannot be predicted. After that, the produced output block would then be operated with the choice function. Okay, it would then be operated with the choice function, so that the bits and bytes inside the row are completely jumbled up. And when the bits and bytes of rows and columns are jumbled up sequentially, so the metric so a hacker or an exploiter cannot exactly figure out where exactly the bit which was initially present could be present now inside the matrix. So this makes the system very cryptographically strong. After the output block produced by the choice function, we apply this function with the big signum function. Okay, this big signum function is used on this block, so that finally this whole process finishes up with jumbling up our columns, so that our final hashed 32 byte block is completely hashed in row wise, in column wise, and in every sense that we can think. Okay, okay, we have received a 32 byte block. Okay, so what happens here is that this is one of the round of the SHA-256 process. So what happens here is that this SHA-256 contains almost almost 1 lakh of these rounds. Okay, almost 1 lakh of these rounds are followed one after another sequentially, so that this matrix becomes so complex and so jumbled up that anyone it is almost nearly impossible for a person to guess, or through the brute force process, guess what exactly would be the final hashed 32 byte key produced. Okay, so what happens here is that once the final 32 byte block is produced, after all the 1 lakh rounds of transformation happens. So what happens here is that this block is then each cell bit of the this block is concatenated to produce a string of 32 bytes, and this string is the final hashed key that is used in our ExCrypt system, which would be further used for the encryption process in XOR and AES mechanism. So basically, this was the whole working mathematics which works behind the SHA-256, and how the SHA-256 uses all these mechanisms to uh, to convert its normal looking password into a very complex 32 byte string key. Okay. Okay, so now we have understand every mechanism, every concept involved inside the SHA-256, and we have seen on paper how SHA-256 mechanism is carried forward through many multiple 100,000 rounds, and how a 32 byte key is produced. So now, after this hashing process completed, now we should look into the encryption process. So the first encryption process used in our system is XOR encryption process, and we will look into how this XOR encryption process is used, and what is the basic functions which are used, basic functions and operations which are used inside this XOR operation to pull off the system efficiently. Okay, so we should go back into our canvas and just start here. So for XOR encryption mechanism, what happens is that for XOR encryption mechanism, we know that our system is chunking the complete input file into small bytes, so that large files could also be handled with ease. So we have chosen the chunk value as 64 kilobytes. As 64 KB is the chunking value, and even if the file is 1 gigabyte, that file would be broken down into multiple chunks of 64 kilobytes. Then those chunks would be broken down into sub chunks according to the encryption technique, and then those sub chunks would be processed one after another to carry out this encryption workflow. Okay, so now, the main crux and the main operation behind this complete XOR encryption mechanism is the XOR binary operation. We know what exactly is the XOR binary operation. It is for any two values. It is A or not of B, and uh, A not of B. Okay, so this is basically the XOR operation. This is basically the XOR operation, and we have also seen what exactly is the truth table of the XOR operation. When the both the inputs are same, so the output is zero. So the output is zero, and if the input is different, so the output would always be one. Okay. So this is basically the truth table of the XOR operation. So this is the crux of the XOR encryption mechanism, and we will see how this basic binary operation is used to transform a big text or image file or video file into a ciphertext that cannot be interpreted or understood by any hacker or exploiter or any common person. Okay, so now let us see how it is exactly done. So basically, what happens is that when we get a 64 kilobyte chunk, so the our XOR mechanism used in our ExCrypt system basically breaks it down into into bytes of 32 uh, into blocks of 32 bytes. Okay, so what happens here is that 64 kilobytes are broken down into many chunks of 32 bytes. Okay, they are broken down into 32 bytes. Multiple 32 byte blocks are created, and then these 32 block bytes are XORed with the key. So what happens basically in the system is that each cell of the key is XORed with the each cell of the 32 byte block of the system. Basically, what happens is that this is our 32 byte data matrix. Let us assume. Okay, this is our 32 byte uh, data matrix, and this is our this is our 32 byte key matrix. Okay, so what happens is that this cell is XORed with this cell. This cell is XORed with this cell with this, and in similar way, each and every cell is XORed, which returns us a ciphered block. Which returns us a ciphered block of 32 bytes, and this ciphered block is then further concatenated with other cipher blocks which are obtained one after another. Every 32 byte chunk is ciphered using this mechanism. So what happens is that these 32 byte chunks are concatenated again and again and again to create the primary chunk, which is of 64 kilobytes. So this 64 kilobyte of chunk is then taken and gets stored inside the output file. Okay, so basically, this is exactly the whole process of XOR encryption. It is very basic. It is very fast. It is yet not very reliable because this mechanism is basically this XOR operation is very evenly known to everyone, and basically the whole strength of this XOR encryption is coming from the randomness of key, and XOR encryption mechanism itself not very strong, because we know that a bit which is XORed with let us say that if a bit which is one a bit value which is 1 is XORed with 0, so we know the output would be 1. If this value is again XORed with 0, so the original output, which would be 1, would automatically be received. So this is not a very reliable type of encryption, because if we take the same key and XOR the original data 2 times, so we will get the original decrypted data, and the encryption process is completely skipped here. So, encryption technique is not considered very secure in this case. Also, when we talk about the authentication one part in this, so we can see if in the authentication or in the network propagation there is any tampering with the key part, if any bit or byte of the key is changed, or any cell position or any column row position changes inside the key, so the same byte or bit of key is not XORed with the same bit and byte of the encrypted or the plain text. So this basically turns the entire encrypted or plain text into a garbage value. So we will not get exactly the output we are expecting, and the complete XOR system fails here. So authentication, security, and integrity is a very big flaw of this XOR encryption system. So after this XOR encryption system, I think we should move to the next encryption system, which is the AES GSM mechanism. So this mechanism is a very advanced mechanism which uses a very complex mathematical algorithm to pull off its encryption process. And a very important thing that is used here is the GCM. GCM is the authentication process. Basically, AES 256 is the encryption technique, and GCM is the authentication technique that is included in this. So basically, as we have seen that in the XOR operation, if any tampering is there, so a person would not know know, and the receiving party, the person who is receiving the data after encryption and decryption whole process is completed, he will not know that exactly this is the data which this is the decrypted data that the original source person was trying to send or not. So it is fast. So the XOR system is fast, yet it is not very reliable. So we will move into AES 256 GCM mechanism. Now, AES GCM mechanism uses basically 256 here stands for the key size that it takes. There are many AES mechanism, AES 192, AES 128, and many other mechanisms. AES 256 takes a 32 byte key, which is exactly the size of the key that we have produced using SHA 256. Okay, so what happens here is that first of all, we know that our primary chunk is of 64 kilobytes. Now, for AES mechanism, what happens is that this 64 kilobyte of chunk is broken down into many smaller subchunks of 16 bytes. Okay, the operating chunk of the AES mechanism is 16 byte. Okay, so what happens here is that this 16 bytes of chunk 16 byte of chunk is arranges itself internally into a 4 by 4 matrix. So what happens is that here is a 4 by 4 matrix, and this 16 bytes are arranged in each of the cell. Okay, in each of the cell, and then the matrices and binary operations are applied on this matrix. So now we will further see what operations are applied on this matrix. So first of all, before discussing the operations of the matrix, there is a very important concept of round key. So we will discuss the round key mechanism. So what happens here is that each round we have a primary 32 byte key, but for each round, we need a separate round key that needs to be XORed with the system. We will see how that round key is used in our mechanism. But how that round key is produced, we are studying it now. So what happens here is that we need exactly 15 round keys. We need exactly 15 round keys for our AES 256 system. Okay, so for producing 15 round keys of 16 byte each, we need 16 byte each of round key. We so 16 by 15 round keys of 16 byte each. So what happens here is that we expand this 32 byte key into a complete different key, and then we will split it into 15 different keys. So what happens is that we basically firstly take this 32 byte key and split it into two parts 16 bytes each. Okay, two parts 16 byte each. Okay, now what happens with this 16 byte of part? These 16 byte of part are again jumbled between themselves again and again and again, so that 16 byte round keys are produced. Okay, so 15 round keys are produced. 15 16-bit round key are produced, and then these round keys are used exactly in the AES 256 mechanism. We will see how this mechanism is taking the round key and attempting it operation. Okay, so now what happens here is that now we will move to the matrix manipulation and operation. What happens to that? So what happens to this matrix 4 by 4 matrix? Okay, so this is our 4 by 4 matrix, and now what happens is that first of all, the first operation that occurs into this whole process is the XORing process. So what happens is that we take our first round key here. Okay, we take our first round key and convert it and XOR this round key with each cell of the plain text or the text we want to encrypt or decrypt. Okay, so what happens, we will take each cell of the round key and XOR it with the each cell or each bit of the plain text, so that it could be converted into a XORed text. Okay, now after this, firstly the round key mechanism, first of all the round key mechanism is used. After that The round key mechanism is only used for the first round. We will see what exactly happens in the other rounds. So after the round key mechanism, there is a substitution. There is a substitution operation. Okay, there is a substitution operation. So basically, what is there is that a table has been created of ASCII values, and we have assigned that how AES 256 would substitute each ASCII value with any other ASCII value. Like for example, the ASCII value of A is 67 and A is 67, and we have set in the AES 256 mechanism that the A's value would be converted. The ASCII value 67 would be substituted with the ASCII value of 119. So whenever this substitution method occurs, so what happens here is that this value of 67 ASCII value gets converted into 119, and then their bits and bytes are further moved into the process of encryption decryption. Okay, so after the substitution process, what happens is that there are permutation processes. Okay, so basically there are two permutation processes which are row shift and column shift. We will see how those row shift and column shift mechanisms occur. And after the permutation process, again the entire matrix 4 by 4 matrix is XORed with the round key. Okay, XOR with the round key, which would further create a 4 by 4 matrix, which is our output of the first round. And this further 4 by 4 matrix that is produced is goes to the round 2, in which the substitution process occurred, then permutation, and then it is again of XOR. So this cycle follows, and total 14 rounds are 14 rounds of this process occurs till till that the 4 by 4 matrix which is produced in it becomes extremely complex and so jumbled and random that it cannot be encrypted or decrypted without the knowledge of the key. So this makes the AES system very cryptographically strong, and its advanced mathematical algorithm makes it immune from the hackers or exploiters which are trying to exploit your personal information. So after 14 rounds of these mechanisms, what happens is that the last operation is that we will in the last operation, what we will do, we will XOR it again with the round key, with the 15th round key. In 14 rounds exactly, 14 round keys have been used, and our 15th round key will be used in the last XORing. And after this last XORing, we will get a 4 by 4 matrix, which would be our final ciphertext. Okay, this final ciphertext will then be concatenated with the other chunks and the other ciphertext which could be produced after XORing, after this whole mechanism to the after this whole mechanism applied to the other 16 byte chunks, and all these chunks would be concatenated to produce our primary chunk, which was of 64 kilobytes. And then the 64 kilobytes of 64 kilobytes of chunk is then written on our temporary file, as we will discuss further how it is written and how the code algorithm actually works. So, we have discussed what is the whole workflow of our AES mechanism. Now we should see what exactly is the substitution process. What exactly is this our substitution process? Okay. So, what exactly is this substitution process, and what exactly is this permutation process that we are talking about? Okay. So when we talk about the substitution process, as I have given a brief about it, so the substitution process here is a table. Basically, a table is made for AES 256 mechanism, that each bit and byte present inside the ASCII value, all the characters, all the spaces, all the special characters, all these are given an ASCII value, and for the substitution process, a table has been made, a rainbow table has been made, in which every ASCII value is assigned to any different number. We know that A has an ASCII value of 67, B has a 68. So basically, when we talk about this rainbow table data is publicly available, and the value of A assigned in this rainbow table is 119. The value of B assigned, should be actually 68, is assigned as 102. So in this way, every ASCII value is given a different substituted value, which brings the randomness and a very complex a lot more complexity into the system, and this process is followed again and again, so that the substitution makes the system extremely difficult to be guessed or using the brute force mechanism. Now, after the substitution process, permutation occurs. So what exactly is the permutation process? Okay, now we will discuss the permutation process. Now, first step in the permutation process is shift row mechanism. Okay, it is shift row mechanism. Now, what exactly is the shift row mechanism? What happens is that in this shift row mechanism is that it is basically the rotation of our matrix, but row wise. So what happens is that the our first row gets shifted by one place. Okay, so this first cell is shifted to the second position, the fourth cell is shifted to first position, and so as the row has been completely rotated. In the second row, the is of 2 blocks. Okay, and similarly in the third row, the shift is of 3 blocks, and in the fourth row, the shift is of 4 blocks, which ultimately brings us the original row only. So this is the process of shift row, which brings the randomness in each column and each row, so that the bits and bytes in these 4 by 4 matrices are completely jumbled up, so that it cannot be predicted by any hacker or exploiter. Okay, so after this operation, what is the next operation? The next operation is the shift column operation. So this is basically the same operation, but with the columns. Okay, so if this is our 4 by 4 matrix, so what happens is there the first column is shifted by one place, the second column by two place, and the third column with three place, and the fourth column with fourth place. Okay, so this cycle is followed in one round, so that our 4 by 4 matrix is converted into a very complex and very jumbled form. Okay, so after both shift column mechanism, what happens is that the final step of the round, uh, which is the XOR process is that we will take our round key, which is also a 4 by 4 matrix 16 byte key, and we will XOR each of the cell of the key with each of the cell of the ciphertext, which is produced after the permutation after the substitution and permutation processes. Okay, this basically concludes a single round, and 14 such rounds are occurring sequentially. At the last, we are XORing the complete 4 by 4 matrix, and this will give us a final matrix X, which is final matrix X, which is a 4 by 4 matrix consisting of ciphertext, which have gone through a multiple matrix operation, multiple superposition algorithms, multiple row transformation, column transformation, and substitution mechanism. All these things occurs parallelly and sequentially inside the AES mechanism to convert the plain 16 bytes, which we got from the input file, into a very strong ciphertext. Okay, so basically this concludes our AES mechanism. We know that these 16 bytes would be concatenated to produce our primary chunk of 64 kilobytes, and that 64 kilobytes would be written into the output file, which is the end of the AES mechanism, which is the end of AES 256 mechanism. But a very important thing we are missing here is the GCM. GCM basically is the authentication process, which is uh, uh, included inside this whole mechanism. So what happens here is that we know that the XOR do not contains any security tag or any authentication tag that could verify that was the data tampered in between during the network propagation, was any personal information was changed or was seen in the network in between the transfer of the packets or transfer of the file. So but the AES 256 GCM mechanism keeps an eye on this, and uses a very strong mechanism, GCM, which which basically keeps the eye on all of this. So to carry out this GCM mechanism, AES 256, this whole mechanism creates an internal context window, which we generally say name as CTX. So what does CTX have? We know that for a 16 byte 4 by 4 matrix, multiple rounds of operation are occurring sequentially, and the final ciphertext is produced after those operations. So what does this CTX contain exactly? The CTX contain mainly 3 to 4 information. First of all, it knows what process is being carried out. Is it encryption or is it decryption? Okay, so this CTX contains the information of what exactly is happening about, and this information gets stored inside the mode byte. We will discuss what exactly is mode byte and how it is written into the output file. So after that, this CTX has the information about the initialization vector. So what exactly is initialization vector? Initialization vector is a randomly generated 12 byte variable which is used to produce a 16 byte authentication tag, which is also stored inside the CTX. So we will talk about the initialization vector. This vector is represented by the Roman 4. Okay. After that, this contains obviously the cipher source code, all the data which has been converted into the ciphertext. All of this information is stored inside the CTX, and at last, the CTX stores the authentication tag. This authentication tag is produced using the mode byte, using the initialization vector and the cipher code. We will look how this tag is produced, and how during the encryption decryption workflow this tag is used to check the authenticity and the integrity, that there was no tampering in the data during its propagation over the network or any local computer. Okay, so what we will do, we know that rand byte is a function which we use to randomly generate the initialization vector, which is 4. Now what happens is that this initialization vector itself goes through a lot of mathematical operations and gets converted into a 16 byte tag. So what happens is this is a 12 byte initialization vector. This is first padded and converted into a initialization vector which is of 16 bytes. We know how the padding process occurs, and there is no loss of data or change of information in the padding process. So this is converted into a 16 byte initialization vector. Now, the 16 byte initialization vector is then XORed by the round key of each round. Okay, what happens is that it is XORed with the round key of each round, and it is XORed with a round key. Then it is XORed with the ciphertext that is produced after each round. We know after XORing the plain text, and using all the mechanisms, substitution, permutation, and all the mechanisms in a particular round, we will get a 4 by 4 matrix, which is our cipher block produced after each round. So then we will XOR our initialization vector with this cipher matrix that has been produced. Okay, and this thing is followed with every round. Every round, the first this output which is produced. This output is also a 4 by 4 matrix. Okay, so this 4 by 4 matrix that is produced is in each round, first XOR with the round key, then with the ciphertext, then next round with the round key, then with the ciphertext, and this process is followed in all the 14 rounds. After all this process is completed, we will get a 4 by 4 matrix which would contain a tag which has information about all the round keys that are used, which has information about all the ciphertext that has been used, which has information about what exactly was initialization vector, and this tag is then further used to check whether there is any tampering in the data, whether any information in the data is changed or not. We will check how this authentication tag is then used to check. So basically what happens is that when our encryption AES encryption process is successful, so what exactly the encrypted file contains? Well, first of all, the encrypted file contains the mode byte. Okay, it contains the mode byte. What exact information the mode byte contains? Mode byte contains the information of 1 and 0. 1 stands for encryption and 0 stands for decryption. So it tells the AES system that whether the process of encryption is going on or the process of decryption is going on. After that, the encrypted file contains the initialization vector, 12 byte initialization vector. Okay, and this mode byte is of 1 byte. Okay, after this the 12 byte initialization vector is there, and after this initialization vector, the complete cipher source code is there. Whatever the ciphertext which was produced after the complete mechanism has occurred, this is contained inside the this is contained inside our encrypted file. And at the last, this authentication tag which we have produced, a 16 byte authentication tag, is added at the last of the file, which is used for checking whether the authenticity of the system was integrated or was maintained or not. So now this is the complete structure of our encrypted file, which is produced after the AES mechanism. Okay, so now let's see what happens when we decrypt this encrypted file. So basically, we get this encrypted file, and first of all, what happens is that the AES mechanism internally extracts the mode byte and checks whether it is encryption or decryption. Okay, so it comes to know that we are processing a decryption process. It comes to know that we have to follow a decryption process. After that, it extracts the 12 bytes initialization vector and stores it inside an array or any kind of container that it wants to. Okay, internally all of these things are stored, and after that this source code is completely converted into the plain text. Okay, this source code is completely converted into plain text, and this tag which was stored in it, this tag is also stored inside a container with maybe an array or an vector, anything else. Okay, so what happens is that after all this process has been done, what happens, this decryption process again takes the mode byte, again takes the 4, and takes all the encrypted data, and the tag formation process which we have seen the mechanism how the tag formation occurs. It again goes through all those mechanisms and uh, forms a new tag and stores it internally into a variable tag underscore new, and it checks is the tag underscore new and the tag same. If the tag underscore new and the tag is same, so that means that there is no tampering in the data between the network propagation or the file propagation. If this tag and tag new are same, so this confirms that there is no tampering, no change of data. The integrity and the security of the system is maintained, and the encryption process and the flow of the data and the decryption process. This entire workflow is secure and carrying over a secure channel. So basically, this is our complete AES algorithm. Okay, so now as we have understood the basic mathematics and the core backend mathematics of how these systems work, as we have seen that there are mainly three cryptographic mechanisms used in our system, which is SHA-256, XOR encryption, and AES-256 GSM. As we have seen that on paper, how these system are using different matrices operations, spreadsheet operations, different binary operations, XOR and or not, and other mathematical operations like concatenation or multiplication. How these mechanisms shape your first plain text into a binary text, then that binary text into a ciphertext, and then that ciphertext, and how that ciphertext is then converted back into your decrypted file. We have also seen how the AES-256 GSM mechanism maintains the authenticity, and how the file and how the encrypted file is stored. What all the information along with the along with the source data which has been entered by the user is also stored into the encrypted file, which we have seen that there is an initialization vector 4, there is a mode byte, there is key, there is authentication tag. These are the things which are also stored with the encrypted file, as we have seen. Now we will see mathematical on paper mathematics is then converted into the coding algorithms, and how those coding algorithms are then implemented into a workflow which can which can work on our files to convert them into the actual encryption decryption workflow. Okay, so now let's deep dive in. Okay, so first we will need to know what is the code overview of the ExCrypt. So first of all, a very important feature of ExCrypt is that it has a modular design. So ExCrypt, as we have seen that there are different mechanisms and different functions. So ExCrypt is divided into different class for that. So first of all, there is a SHA-256 class. The SHA-256 class maintains the mechanism and the algorithm of SHA-256 and basically include it into our C++ ExCrypt system. Okay, so SHA class handles all the working of the SHA class and all the related utilities and all the related functions that need to be included in it. Okay, after that there is an XOR encryption class. So XOR encryption class maintains how the hashing process, how the hashing key would be imported into from the SHA-256 class, how the hashed key would be imported into the XOR encryption class. That XOR encryption class would maintain the encryption and decryption process. It would maintain the authenticity tag. It would maintain that the code could not be tampered, and all the functions that are related to the XOR encryption mechanism are maintained in the XOR crypto class. Okay, so then there is also AES 256 GCM class. So the AES crypto class maintains that all the functions related to AES-256, like generating the initialization vector, creating a mode byte, creating the ciphertext, creating the authentication tag, also creating a cache memory, and everything related to the functions of the AES GSM. Either it is encryption, decryption, authentication process, either it is any kind of file header making, or creating a complete structure of the file is all handled into the AES GSM class. Okay, so after that, this code is divided into further many functions, like there is a dedicated encryption function which derives all these classes. It uses the SHA-256 class, it uses the XOR class, it uses the AES GSM class, and imports all the code from these classes, and use them into a function, which can then use all the related functions or all the related variables that it has to use to complete the workflow of the encryption, complete the workflow like this: that importing the file, that encrypting that file, that storing that file into a particular folder. This whole workflow is carried out by this encryption function. Similarly, there is a decryption function which handles the workflow of importing all these classes using the objects of these classes according to the oops concept, and then opening the file from that encrypted folder, using that file using the path specified by the user, taking the password, generating the key using the classes objects, and then decrypting the file to store it into an decrypted folder, as we have mentioned it into the system. Okay, so this complete thing makes the design very sophisticated, and the code very much more clean, and much more presentable and code friendly. So the code also create many utility classes which we will see further in the class, they help uh, how they help the system, and how they enable the workflow to handle smoothly. They handle the edge cases, they handle the error handling, they handle any other vulnerability or any other problems into the system. Okay, the second very important thing into the ExCrypt system is the code security. As we know that as we know that while using this encryption decryption system, it is very important to not leave any kind of traces behind, which can leak the information of this encryption system, which can make the system itself vulnerable, which can be exploited by hackers or exploiters which are present online. So it is very important to handle every variable and every heap memory or every dynamic memory with very much care. So okay, so we have ensured that every heap memory, every dynamic memory, every variable, every array, vector, and everything is deleted and properly managed so that there is no memory leak or no value leaks into the code, which can uh, which can even waste the memory and also leak the personal information of the system. Okay, so this manages the code security of the function of the system, and the code security of the system is also enhanced by the error handling classes of error handling functions and the classes of the system, which handles that every temporary file or every file that has been unsuccessfully encrypted, or there is a wrong password entered, or the file path is wrong, or any other kind of obstruction which is caused during the encryption or decryption process. So these code security and these utility classes help to avoid all these memory leaks and make the system strong and integrated enough to make a secure environment in which the files and folders could be encrypted safely. Okay, so now first let us discuss what all libraries are we using into this. So first of all, a very basic C++ library is IOStream. We include it in every C++ code. It is the basic library of the C++. It contains the basic terminal input-output commands like cout, cin, crr, which is used for error outputs, and flush, which is used to push the output into the terminal. Okay, so it contains many other functions, and it is the basic library that should be included into the C++ code. After that, we are using Xstream library. Okay, so Xstream library basically brings the concept of file handling into the C++. All the functions, operations which we think of in file handling, are brought into the C++ by Xstream. What do we mean by file handling operations? File handling operations basically means that we are bringing a file into a C++ terminal. We are opening the file. We are able to read the file. We are able to edit the file. We are able to make any changes into the file, append, write, or any other changes which we have to make into the file. And finally, outputting a file into any other name, or formatting the same file, and etc. etc. Many other functions. So basically, we are using two main functions from the Xstream library here. We are using the Xstream and Offstream functions. If function is basically used for reading the files, and off-stream function is basically used for appending and writing the file. And a very important thing is to be mentioned is that every file used in the ExCrypt system is opened in the binary mode, because it is very important that when we are dealing with encryption decryption, so every file should be opened in binary mode, because we are dealing with bits and bytes. We are When we discuss the mechanism and the mathematics, we have seen that how many binary functions and how many different type of binary operations are done, of XOR, of NOT, or any many other binary functions are done on the encrypted text. Okay, so it is very important that all the data which is coming into the encryption mechanism and the encryption functions is a binary function, so that it could be handled properly. Okay, after that we are including array library. So the array library is important to be included to include many array functions, to know the size, functionality, to know the pointer address, and many other functions which include in the array library, so that we could properly use the container tag array present in the C++. After that, we are using the vector library. The vector library is very important in the C++, because it provides us a dynamic container. Like array is a static memory container, whereas vector is a dynamic memory container, include which can include many different which can have a many more applications than an array, like changing the size of the vector, or defining the size of the vector at the runtime, and many other functions could be performed using vector and the dynamic memory, which are impossible to be occurred using the static memory. So we are including the vector library. After that, we are using the string library. String library is basically used for including the firstly the string data type into our C++ system, and many string functions which come along with it. Many string functions like counting the size, iterating the strings, and manipulating the strings, changing their cases, and many other functions, inbuilt functions which come along with in the string library to manipulate the strings, our passwords, our paths, and many other things which we can manipulate using this string library functions. Okay, after that we have included the file system library. The file system library is very important in the system for maintaining the integrity and security part of the system. As we have mentioned, that in the security part we have managed the edge cases or the different kinds of errors which can occur in the system. All these cases are completely tested and handled. So these all functions are some functions are inbuilt and some functions we have made. So these functions are came from the file system library. File system library contains many file manipulation and file information getting functions, like file existence. We can check if this file exists or not. We can handle errors according to it. We can check the size of the file which is used to which have been used in the system to display the progress bar in the system. We can delete the file if it is corrupted. We can delete the file if it contains any malicious data, if it is tampered. We can and many other edge cases which has been handled into a system, which we will further discuss in the video. Okay, after that we have included the C string library. C string library is basically the C string library functions are not directly used in our ExCrypt system, but the OpenSSL library, which we are going to discuss in few moments, uses the C string library. So basically, is that the OpenSSL library is written in the C language, not in C++ language. So it uses many C string functions, and these C string functions and these encryption mechanisms which we talk about are basically coded in the C language, and it implicitly uses those functions to perform its encryption internally, and maintains the integrity and authenticity of those functions and mechanisms in the OpenSSL library. So it is very important to include a C-string library. After that, we have included the algorithm library. Algorithm library is used to make manipulations and changes and iterations into the container tags, like arrays and vectors, which we have included. It is used to manipulate and do some changes, like minimum and copy functions are used in our ExCrypt system. These functions are used in the system to make manipulations into the containers and enhance the functionality of the system. Okay, so now as we have discussed our standard libraries of C++, now we will look into the most important library, which is the OpenSSL cryptographic library. So for some historical context, OpenSSL cryptographic library was first made in 1998, and it is a collection of many different types of things. Basically, cryptographic mechanisms are a very small part of OpenSSL library. OpenSSL library deals with many aspects of networking, encryption, cyber security, and network integrity in maintaining the network flows. So basically, OpenSSL deals with the HTTPS request network systems, which was written in the C language in during 2000s to 2005s. It also deals with different the AES mechanisms and the different RSA, AES, and different encryption mechanisms which are written inside these OpenSSL libraries in C language, which was written in 2011 2012. It also contains many hashing algorithms, SHA-256, SHA-128, and Decrypt, and many hundreds of hashing algorithms which are commonly used nowadays. Okay, so basically it deals with the networking concepts, which is the TCP/IP protocol, HTTP protocol, mail email protocol, and many other protocols which handle the your internet traffic. And also it deals with the encryption of those packets. Like when we say that the network packets are traveled over the internet through different choke points. So it is very important that those choke points are secured, and the data reaching those choke points is encrypted. So OpenSSL basically keeps track of all these things, and it contains more than 10 lakh lines of algorithms, codes, and many different mechanisms which are written inside it, which are used in managing the network traffic, as well as the cybersecurity and cryptographic mechanisms written into this library. Okay, so now let us see what exactly headers and what exact libraries we have included from the OpenSSL. Okay, so first of all is the OpenSSL evp.h. So basically the OpenSSL contains many mechanisms. So it requires a proper API key, so that we can call the OpenSSL library in properly. Like it contains hundreds of encryption mechanisms, hundreds of hashing mechanisms, hundreds of protocols, and all their code written. So it is very important to properly manage them and call them with proper code. But if we write them manually, it would create a lot of confusion and complexity into the code. So OpenSSL contains a high-level encryption API key, which is set as EVP. So for calling this EVP, for calling this interface of API, which contains the backend code of all these functions, all these mechanisms, and all these protocols. So this EVP contains all that code organized into an interface. So to call this interface, we use this OpenSSL /evp.h library. Okay, so after that, there are many functions which are included into our ExCrypt system from this EVP library, as some of them are mentioned here: EVP, Cipher, CTX, New for creating a new cache memory, CTX, EVP encrypt initiate X for initiating the encryption process, EVP encrypt update for updating the encryption process, and so on and so. We will mention all the functions from which library they are and what are its function later in the part when we will discuss the code line by line. Okay, so this library also contains many constants which are used in it. Like one of it is mentioned here is EVP max block length, which tells us that what is the max block length, that basically the chunking length which is being used during the encryption process is stored inside this constant, which has already been mentioned as 16 bits, sorry, 16 bytes. Okay, so basically this library handles the basic structure of the encryption decryption mechanism in OpenSSL. Okay, after that is the OpenSSL sha.h. So basically I have told you that the SHA secure hashing algorithm is a class of many hashing algorithms. It contains SHA 128, SHA 192, SHA 256, and many other SHA, which which contains of many different types of mechanisms and some other hashing techniques also. So this OpenSSL sha.h is basically the compilation of all those codes into a under a single library and a command. Okay, so this OpenSSL library is used to import the mechanism and code of SHA-256 to hash the passwords in our ExCrypt system. Okay, so after that we have included OpenSSL crypto.h. So what exactly this OpenSSL crypto.h does? It is used to maintain the integrity of the system. As we have talked that during the process of encryption and decryption, it is very important that all the variables and the memory created, it is very important to clean them, so that no traces of the encryption decryption or any vulnerability or any integrity flaws are left, which could be exploited, which can be further exploited by the hackers or exploiters on the internet. So OpenSSL cleans. function is a very important function which is used in the ExCrypt function, which is part of this crypto.h library, which is used which keeps a check of all these. It keeps the check that all these variables, all these memories which have been created into the heap at the time of the processing or the encryption process are cleansed at the end of the end of the encryption or decryption process. So it maintains the integrity and security of this encryption workflow. Okay, so after that, we have included OpenSSL rand.net. Okay, so what basically this library does is that we have seen that when we talk about the initialization vector, initialization key of our AES mechanism, which we said say as 4, Roman number 4. So that is randomly generated, every time randomly generated, which can make the password or we can make the encryption process undeterministic. So any hacker or any intruder cannot determine that what randomly generated key has been used into this system, what vector has been used to initialize the system. Okay, so a very important function which is included here is rand bytes. So this function is uses the entropy method. Now let us talk about that. We can also use the random library also for this, but when we talk about the engine that the random library use is very deterministic and can be predicted by the exploiters and hackers, and all the code of those random engines has already been cracked by the hackers. So it is very unsafe to use it as our random generator, random initialization vector generator. Okay, so we use rand bytes, which uses the hard disk and the pre-existing memory of the functions and passwords already used in our ExCrypt system, and it uses the entropy method. It uses the past data and the future possible values, and it organizing all of them into the tree and into the tree structures, and then those passwords are then filtered out to create a truly random value which cannot be determined, and is very random, which is very cryptographically strong and cannot be determined as the random engines in the random library. So bytes function is very important for our initialization and maintaining the security of the AES mechanism. So it is used in this system. Okay. So now let us move into the coding part now. Okay. So first we will talk about the SHA-256 hashing class. Okay. So we have already talked what exactly is hashing and what and how hashing is different from encryption and decryption. So we have mentioned those points only, that hashing is an irreversible process, not as encryption decryption. It is used for key generation from a password in our ExCrypt system, and it maintains the security of the system by key generation and removes the deterministic part or the guessing part or the predetermined passwords that are commonly entered by the users, determined by the hackers, so that they cannot use the commonly used password to decrypt your file. Okay, so it maintains that randomness, so that the integrity and the security of the files and the password is maintained. Okay, so let us now look into the hash class. Okay, so first of all, we can see that hash class. Now, I think let us move into the VS Code and see in that. Okay, so now we are in the VS Code, and this is the whole code of our main.cpp file. This is our folder, and it contains basically two folders: encrypted files and decrypted files. These folders are themselves encrypted, so that the files in them cannot be easily seen without the password. And it is very important to see that encrypted file, after we have taken any text file and encrypted it. So that file would be automatically stored inside this encrypted underscore files folder. And whenever we write the name of a file, a file is automatically derived from this encrypted files folder, and after decryption process is directly stored inside the decrypted underscore files folder. Okay, so this is an automatic process which have been integrated into a system. Okay, so here are all the libraries that we have included. We have already talked about. Now, what exactly is this part then? What exactly is this part? When we talk about this part, so this part is used for different system integration. Now, this system we know that every system needs integration, either it is Windows, Linux, Unix, Mac OS, or every system. This ExCrypt system should run. It is very important for it to maintain the different platform variability, so that it could be used by everyone. Okay, so this code part maintains that. Okay, so what it say, if definition underscore win32. Okay, so this condition checks that this is a header condition which checks that is your operating system which you are using is of Windows or not. If it is of Windows, so it would include two of the libraries which are windows.h and conio.h. We will further look what is the function of these two libraries. These two libraries are used in the password security. We will see how they are used in the password security. And similarly, it is like a if else block. The else block contains the commands of terminals.h and unistd.h. These two libraries are similar libraries for windows.h and conios.h for the Linux or Unix system or Mac OS system, because all the three are designed on the Unix system only. So these are the libraries which are included for Windows and for Linux Unix system. So it maintains that all the that this ExCrypt system works on all the systems and do not only works on Windows or only on Linux systems. Okay, and if it is the closing tag of the if else definition command block. Okay, so it is very important to put first the start of the if definition and then else and then end if. Okay, so it is very important for it to be included. It's the basic C++ syntax. Okay, so then we have included using namespace std, using fps. It is just for avoiding the std underscore and std one format, which would increase the complexity and increase the manual writing part of the code. It has been included to for using the standard names while writing the code. Okay, so what exactly are these folders path? Okay, so these folder paths are the encrypted file folder part. As we can see that these are the encrypted file and decrypted file, as we have talked here. The encrypted file and decrypted file folder which are existing inside the cppa project folder. Okay, so these are the folders in which the file come. The normal text or normal image file comes, and then after encryption stored in the encrypted files, and after decryption gets stored into the decrypted file. So these are the paths, and these paths would be further used for storing this thing, and we will see where they are used and how they are used to follow the command as we have mentioned. Okay, now what is this chunk size? Now, as we have mentioned, the chunk size, as I have mentioned you that for large files it is very important to break those files into chunks, so that those files can be properly processed. Okay, if we give a 1 GB file directly into the encryption mechanism, it could get confused, and it would just take a lot of time to complete the encryption process, which would be very inefficient, unoptimized, and would increase the complexity of the system. Okay, so we what we do, we break the files into chunks. Okay, chunk number one, chunk number two, and so on, till all the complete file is broken into chunks. Then those chunks are decrypted, and further those chunks, when all the chunks are encrypted or decrypted, then those chunks are concatenated, and then those chunks gets stored inside the files. Okay, so we have set the chunk size as 64 kilobytes, because this is a standard which has been set mostly inside the encryption decryption system, because it is neither too small to take a long time, and it is neither too large to make the to increase the complexity of the system. Okay, Okay, after we have seen after we are seeing this hash class and the hash mechanism which we have discussed with the mathematics of the hash mechanism, we are implementing it here inside our system. Okay, and before discussing these classes, a very important thing is that to discuss why exactly we have not manually written all the code, and we have imported these mechanisms inside from the OpenSSL library. So OpenSSL library has been working from more over 20 years, and the code and the mechanism written inside it, either it is easy or difficult or mechanism, it goes through hundreds and thousands of iterations. So these encryption systems and the encryption mechanisms run on the systems that have very high capabilities, because like we talk about SHA 256, we have seen that it goes per iteration for 100,000 rounds. Okay, so this makes it very complex to write the manual mechanism into our system. And also a very important thing to be noted here is that uh, when we write the manual mechanism here, so the integrity and the safety part is also violated here, because the OpenSSL library has been actively tested by many industry experts, and they are and they have checked the security and integrity part of the OpenSSL library mechanisms, which could be directly used in our system instead of writing the mechanism manually. Similarly, for the XOR class, even though the XOR encryption and binary mechanism is very easy, we have seen it how easy it mathematics is, but still we are using it here. But still but still we are and we know that the XOR class mechanism do not go through a lot of iterations, and it only goes through iterations of the keys, which is 32 bytes. So here we have used the XOR crypto class as manual mechanism, and we have not included the OpenSSL mechanism of the XOR class. So we are taking the mechanism from the OpenSSL class only for those who demand very high capabilities of the system, and goes through hundreds and thousands and millions of iterations to pull off their processes. Okay, so we have written the XOR mechanism manually, and similarly we have imported the AES mechanism and its integrity and authenticity tag one process from the OpenSSL library, because first of all it increases the complexity of the system very much if we write it manually, as well as it also violates the security part also. If we are using any system for security purpose only, so it is very important firstly that the system itself is secure. If the system itself is vulnerable, so it cannot be used for securing the other files or folders. Okay, so firstly, so we are directly importing these functions, and we have looked into the mechanisms and the mathematics of these functions manually. Okay, so now we are using the algorithms and codes written in the OpenSSL library and importing it into our ExCrypt system, so that our ExCrypt system works properly. Okay, so now let us move back into the hash class as we were discussing earlier. Okay, so now we have defined here hash class. We are defining the complete class in public. There is no private variable or any function. Okay, so in the hash class we have defined a function which is SHA-256. It is a user-defined function. Small SHA 256. It is a user-defined function which takes the input as a pass by reference of the input here what exactly is input. Input would be the password that would be coming. We have written the code of this input inside the main int main function, and in the encrypted function we will look into it further in the code. And it takes the input from the input as the password, as the pass by reference, because we do not want that there is any memory leak and the password itself gets replaced, so that the password just gets lost, and any hacker or exploiter cannot know what exactly was the original text password which you have given was. So it takes a constant string password reference input password, and returns a string which is the 32 byte key which it returns. Okay, so now then we have mentioned an array hash which has unsigned character data type, and we have taken a constant from the OpenSSL library which is SHA-256 digest length. Okay, what exactly is SHA-256 digest length? It is the length that the SHA-256 would be returning as the output. So we know that SHA-256 returns a 256-bit password or 32-byte password. So the length of the SHA-256 digest length is 256. We can manually enter 256 also here, so it would also return the same workflow and process. But we are leaving it like this only because it is the standard of the of the OpenSSL library. Okay. After that, we are using a function which is SHA2 capital SHA256, which is the standard pre-built function in the OpenSSL library. Okay, so what exactly are the parameters of this function? Now, first we have to discuss what are the parameters. So, first of all, this function takes the input. First parameter is the input as a pointer function. So we know that input is a string as mentioned in the parameters of the definition of the user defined function. Okay, so we can see that this we are reinterpreting casting the input from string into an array of not into an array into a vector of constant unassigned character pointer. Okay, so what exactly is input.data function doing? Input.data function, what it does is that it like first let me start from the start, that this reinterpretation cast changes the input from string into a vector. And what does this input.data do? It points to that vector. Like that vector gets stored inside the heap or the dynamic memory, and that input.data function is defining the pointer that is pointing towards this vector inside the heap memory. Okay, so input.data stores that pointer. Okay, after that, the second parameter of this function is the input.size. Input.size, the size of the password which is getting inputted. So input.size is just a function inside the string library, and dot data is also a function of the string library. So these both functions are string manipulation functions. Input dot size tells the size of that string, and after that, what is the output vector, which where the vector or array where the hashed file has to be stored. So we have entered hash as we have made our array hash of 256 bits. So that is the third parameter of the SHA-256 function. Okay, so after that we are again explicitly converting the return type of the function. We are returning return string. Although hash is a array, but we are changing the types from array into a string by concatenating all of its block all of its sections and blocks into a single string. So what it is doing is that what does the string function of inside the string library does? It takes the array or a pointer or a vector to which it is pointing. So what are its parameters? It takes a vector and the length of the vector. It takes both the things and concatenates all of its value into a single string. So we know that it is a 256 bit array, and so it gets converted into a 256-bit string, which is then returned as a hashed key from this whole function small sha 256. Okay, So this is exactly the workflow inside the SHA class. It converts it converts the password which is being inputted as input, which is being inputted as input, and then using the pre-built function SHA-256 to convert it into a hashed string. Okay. Okay, so now let us discuss the XOR crypto class that he has made. So now, first we can see that its name is XOR crypto, and then we can see that we have defined some private variables inside the XOR crypto class. So why is it that we have defined the key and position as private variables? Because it is very important that to protect these variables from getting lost or getting into hands of any person using to exploit the system. Okay, so we know that key is a very important thing that has been created by the hash class using the SHA-256 mechanism. And if this key gets into hand of any person who is trying to exploit your personal data or your encrypted decrypted files, so that could be very damaging. So these variables are defined inside the private variables, so that their access is restricted to any part of the code except this class. Okay, so now in the public variables and methods we can see that a constructor is mentioned which takes up key as a parameter during the time of object making for this class. Key should be entered as a parameter as a parameter for the object making. Okay, so this constructor basically assigns the value of key to the private variable key of the class and the positions value as 0. Okay, there is also a public method mentioned inside the class which is void encrypt decrypt. Its return type is void, and it takes up a data pointer. What exactly here is a data pointer? Data pointer basically is a pointer which points towards the data which has to be encrypted. Okay, so that data, we know that we have broken the data into the chunks, and those chunks are stored inside the heap memory. So this function basically calls those pointers, uh, and then put those pointers through this mechanism, so that they get so that each and every bit inside those chunks uh, gets encrypted properly and are returned in a proper format. Okay, so what are the parameters? First of all, parameter is the pointer of the input data, and second is the length of the input data. So basically what happens is that we know that the data could be of if we have chunked for 64 bits. So for the last part of data, if we have chunked all the parts, but let us assume that after chunking all the parts, the last block which has to be formed is only, let's say, 36 bits, uh, 36 uh, 36 kilobytes. So that would create a error into the function, and so this edge case has to be handled very professionally, and that is why this len variable has been included here, so that that edge case could be handled here. Okay, so now the data and each bit inside the data goes through this loop where each bit, which is data bracket I, is XORed is uh, XORed with the key position modulus of 32. What exactly is position modulus of 32? We have seen that position have already been assigned the value of 0, and in the loop we can also see the position plus operation. So with every iteration, the position value will increase by 1, and we know that key is of 32 bytes. So what happens is that the first byte of the first byte of key gets iterated with the first bit of the data. The second byte of the key gets iterated with the second bit of data, and so on and so forth till 64 kilobytes, or whatever the chunk size is there. Chunk size is, the values are iterated till that. Okay, So in this way, the data that was consisting of the plain cipher text, consisting of the plain text inside it into the dynamic memory, is now converted into the cipher text according to this mechanism of XORing it with the each byte of the key. Okay, now when we talk about, as we have discussed, that XOR is a function which can encrypt and decrypt the plain text into ciphertext and ciphertext back into the plain text with the same operation only. We do not need any separate operation or the separate mechanism to write inside the code for doing so. Okay, so if we have a if when we store when we talk about the decryption workflow, so now this data, which is one of the parameters, is now is now pointing towards the encrypted chunked blocks. Okay, so now this data is the chunks of the encrypted files, and now these chunks are again entering into this loop and getting XORed one by one by the bytes of those keys only, Okay, so what happens here is that they get XORed by the same key, because the password entered by you during decryption is checked, and if that password is same only, so the key generated by the SHA-256 will also be same, and hence the same bytes, the same key position bytes would be again XORing with the same bit of the data, which would resulting back into the original data inside the data pointer and getting stored into the dynamic memory. Okay, so in this way, after all the chunks are decrypted, they are concatenated and again written into the decrypted file. Okay, so in this way, a single loop can handle both the plain text to ciphertext mechanism and ciphertext to plain text uh, mechanism, just by a single for loop. Okay, now let us talk about a very important flaw in the XOR mechanism, which is why have also included the AES GSM mechanism. We know that XOR mechanism is very fast because the XOR operation is one of the fastest operation that a computer can handle, because it takes uh, bits which is directly understood by the computer, and it also returns bits, because XORing is direct function is directly written inside the registers of the computer, and this operation is one of the fastest. So this mechanism is very fast in comparison to AES GSM, but it is unreliable. So basically, what happens here is that when we are talking about XOR mechanism, so XOR mechanism will take a password. Let us assume that we have encrypted a file using the password 123. Okay, so it 123 would be converted into a 32 byte password using the SHA-256. Then that SHA-256 key that has been used during encryption would take each and every byte of that 32 byte key and XOR it with each bit of the data. Okay, which is present in the plain text file. Okay, now we through this process we will get the encrypted file. Okay, so now this encrypted file, when we are starting to decrypt it using the decryption workflow, so if we have entered the password 12345, let us assume, if we entered the password 12345, so 12345 would create a completely different 32 byte key from the 123 using the SHA-256. So now the values which are going into the key position, using the key position, so the bytes so the data bytes which which were earlier used with a particular byte of the key during the encryption process gets altered, and they are altered, so each data byte is not XORed with the same byte which it was XORed earlier, so it does not return the original data and gives any garbage value during output. So okay, so this value can be tampered very easily in between. Okay, so if any person wants to enter your line and tamper your data, this data is still unreadable, and in the binary file, the encrypted file is still unreadable. But the tampering of data in between the line, if any person just tampers even a single byte or a single bit, also your whole file would be corrupted and would return a garbage value. This would make the system completely flawed, and would basically end the purpose of the whole system. Okay, so basically this is a very big flaw of the XOR mechanism. That is why we are using more advanced mechanism like AES crypto, which also contains authentication tags which check the tampering of data or changing in any bits, or verifies that you have entered the same password or not. All these things are kept in concern in AES 256 GCM. Okay, so now, after the XOR encryption mechanism, we are going to look what exactly the AES crypto class that which implements the AES mechanism and calls the AES mechanism from the OpenSSL library does. So we can see that the class name is AES crypto. There are some private variables defined into the class. You can see that there are two private variables. First private variable is key, and then second is CTX. CTX pointer. So what exactly, as we have seen in the crypto class also, sorry, we have seen in the XOR class also, that key is kept private because key is a very key detail that cannot be compromised or cannot be left into the memory, or can be accessed in any part of the system, so that hackers or exploiters can use it to encrypt and decrypt your files. So the key must be strictly kept into the private variable so that it cannot be accessed anywhere into the system. Okay, what is this CTX? So as we know that in the AES 256 GCM mechanism, we have seen that there are many things that needs to be that needs to be considered during the encryption process also, during the authentication tag creation process also. So there are many things like mode byte is there, initialization vector is there, there is authentication tag, there is the cipher text, and there are headers also included in this. So what is the CTX? CTX is the cache memory of the AES encryption method. Now what do you mean by cache memory? So basically we have seen that the file is getting chunked in 64 kilobytes of blocks, and we have seen in the AES mathematics that AES mechanism further change those chunks into 16 bytes smaller chunks, so that it could process it, because its mechanism is written in 16 bytes chunks only. So after that, what happens is that whenever a chunk starts, whenever let's say a 64 kilobytes of chunk starts, so what happens is that a CTX, which is the cache memory, is initialized. Okay, so what this CTX stores? First of all, the CTX stores the mode byte. It stores the mode byte, that what exactly is happening. Is it happening encryption, decryption? Is it happening encryption or decryption? It stores according to 0 and 1. Okay, after that it stores the initialization vector. Okay, it stores the initialization vector which is generated. After that it would encrypt each 16 byte chunk that has been encrypted by the AES mechanism, and then store that continuously, so that they all can be concatenated into a perfectly 64 kilobyte of primary chunk that we have set into the system, 64 kilobyte primary chunk. Okay, after that this whole chunk gets transferred into an output file, and the cache is deleted. It is very important to delete this cache because it contains very vital information. It contains key, it contains the information about the initialization vector, it contains authentication tag, and every other detail that can be used to exploit the data entering into the system. So it is very important to delete this CTX. So this CTX is set as private variable and is only accessible inside this class. And this CTX is mentioned in such a way that every time this class is initialized or called, this CTX is made and then automatically get destroyed. We will see how it is getting initiated. Okay. So first, we see that in the public variables and methods, first then constructor is design constructor is made. Okay, so we know that a constructor is called whenever a class object is made. Every class object, whenever it is made, before making any variables or before making any methods or implementing any methods, first the constructor is called in any way, whether it contains any parameter or not. First of all, the constructor has to be called by the class. Okay, so first of all, what happens is that the constructor takes this key, and this key is then stored inside the private variable key of the class. Okay, the key which is entered as a parameter as a pass by reference in the constructor is the key that would be entered and coming from the SHA-256 hashing class. Okay, so after that, when the key is assigned to the private variable key, after that what happens, we are assigning CTX. Okay, now how CTX is assigned? CTX is assigned using a in built-in function in the OpenSSL library, which is the EVP cipher CTX new. What it creates? It creates a new CTX cache memory. This CTX cache memory will store all the data. As I've mentioned, it could store mode byte initialization vectors, the chunks of the memory, and then concatenate it to form a primary chunk, so that it could be stored into the output file. Okay, so what happens here is that a CTX making the CTX inside the constructor is that whenever the class object is made, the CTX is always formed, because CTX is very important for the AES mechanism, and it cannot be ignored. If we enter it if we make it as a normal method, it could be in some case that we forget to call the function which makes the CTX. So that could create a very big blunder into the system and return a garbage value. So it is very important that it is written inside the constructor that every time an object is made of the AES crypto class, the CTX is formed by its own only. Okay. Also, one thing is the error case handled here is that if the CTX is unable to form, if not CTX, if the CTX is empty or is unable to form, it will throw a runtime error. Will throw a runtime error which is failed to create a cipher context. Okay, so this cipher context is very important, and if it is not created, the AES GSM mechanism will completely collapse. Okay, so if this cipher context is not made, the program would be terminated and throw a runtime error. Okay, after the constructor, a destructor is also given here. So it is very important that I have told that it is very important that this key, this catch context, this cipher context is very important to get deleted after every object made, or every block encrypted, so that the information do not leak into the hands of hackers or exploiters. Which can use this information key, authentication tag, initialization vector, and different information to exploit your system and your files, your encrypted and decrypted files. Okay, so what happens is that this destructor checks that if the CTX exists after all the functions of the class are initiated and used, after the function of the object is over, and we are going to complete the decryption process and close the object. What it will check, if the CTX exists. If the CTX exists, it would free the CTX space and delete it. So it is using a built-in function which is EVP cipher CTX free. So what it does is that it frees the CTX or the cipher context window, and all of its cache memory is deleted and lost. It can never be retrieved or found by any hacker or intruder which is trying to get the information of your system. Okay. What happens after this is that it is very important that many variables are also formed and deleted during all of this process of encryption and decryption. So it is very important after the cache is deleted. The cache contains the ciphertext, the key, and all things, but still some variables or some heap memory, some dynamic memory could be existing into into the context window, or into the encryption process window. Okay, so what we it does is that you use OpenSSL cleanse function. What it does is, first of all, it cleans all of these left up heap memory, dynamic memory. And a very very important thing that it does is that the key which is stored inside the memory, which is still stored inside the memory of this class, even though it is a private variable, it's still very important to clean it up. So what it does is that open ssl cleanse function, so the built-in function, takes the pointer of the key which is stored inside the heap and dynamic memory. I have told earlier also that key.data returns the pointer pointing towards the key variable inside the heap memory. So key.data, which is the pointer towards the key heap memory, it gets deleted, and it takes the size of the heap memory to be deleted. So we know that it is 32 bytes, so it takes 32 bytes and deletes the key. So what all is deleted? The cache window, the context window, the cipher context is deleted, the key is deleted, and every other variable that is made in between that can tamper or leak the information of the system is deleted. So every edge case and every possible error causing variables or materials are properly handled into the system and deleted as per their requirements. Okay. Also, one thing to be noted is that these all are mentioned inside the destructor. So destructor is always called, whether the class function fails in between or it gets successfully implemented. The destructor and constructor are always called. So the creation of CTX context window and cleansing of the encryption decryption window is always done. But whether the encryption decryption is successful or it is unsuccessful. So okay, so now let's move ahead and let's see the functions and the methods which are defined inside this AES class. Okay, so now first method is bool init encrypt. Okay, so what exactly this bool init encrypt does is that it takes a initialization vector. Okay, the pointer of an initialization vector, this constant integer character, star asterisk 4, is the pointer to the initialization vector which we are going to create in this set tag function. Okay. Okay, so what it does is that this set tag function makes a initialization vector. Okay, makes the initialization vector, and after that this initialization vector, which is created using this set tag function and the randombyte function which I have told you earlier in the libraries part. These both function make the initialization vector, and this initialization vector is then sent into this init encrypt function, which further uses a built-in function which is evp encrypt init underscore ex, which creates a encryption window. Like first of all, a cipher context window is created, which will store all the information of the functions which are happening, what the information is being stored, and it gets stored in the ctx window. But it is very important that the 16 bytes which the AES mechanism is receiving, so those 16 bytes are properly managed. So it creates a special encryption window, which is created using this function. Okay, encrypt init underscore exe. So what does it takes? The parameters of this function is first of all the cipher context to store the information all the information that happens inside this encryption window to get stored into the cipher context. After that, it takes what type of encryption we are doing. This is the function that defines what type of encryption we are doing. We are using AES 256 GSM mechanism, so we have to mention that. After that, we have to mention that what exactly is the memory that is being located during the initialization. So here, as here we do not have any initialization till now, so we are putting null pointer. That means there is no initial memory in this encryption window, and we are starting a new refreshed window. Okay, so after that, after the next parameter is the key data. So key data gives the pointer of the key that has been created by the SHA-256, which is used inside this encryption window, and the 4, which is the initialization vector. So what happens is that it takes the context window, it takes the type of encryption it needs to do, it takes the key, it takes the initialization vector, it takes everything, and it just starts a encryption window where the further encryption process will occur. If the process of creation of encryption window is successful, so this function returns 1. So that is why we have done return equal to 1, because the type of this function init encrypt is bool, so it would return true or false. Okay, so this evp encrypt init underscore ex returns 1 whenever the encryption window is successfully created, and returns -1 when the encryption window is unsuccessful to be created. Okay, in a similar way, the bool init decrypt window is also created during the process of the decryption workflow. Okay, so we have set another function which is init decrypt, which also takes the initialization vector during the decryption workflow, and it also calls the function built-in function evp decrypt init underscore exe underscore ex, and all the parameters of both the functions are same, and returns the same 1 and -1 as mentioned in the above function, also same, similar to that only. So after all of this, when we are talking about the encryption workflow, so what does this function does? It initialize the encryption window, and init decrypt function during decryption workflow, it initialize the decryption window. So after initializing the encryption window and the decryption window inside this hypercontext, what is the next step? Is that the next step is to take the chunked part of the files, which is 64 kilobytes of chunks, and break them into 16 bytes of sub chunks, so that these chunks could be further inputted into the AES mechanism, and go under processing of the AES mechanism, because we have studied that AES mechanism takes the values in the chunk of 16 bytes into a 4 by 4 matrix, as we have already discussed in the mathematics of AES mechanism. Okay, so this process of chunking and processing the mechanism further using all the mathematics that we have discussed is done using this user-defined function, this which is update encrypt. Okay, so what happens here is that it takes basically three parameters. First of all, it takes a pointer in. Okay, what this pointer in contains? The pointer in contains the 16 bytes of data that we are giving it. So the after completing the chunking process, we get the 16 bytes of data that has to be encrypted. So we input the pointer of the memory where these 16 bytes is stored, and which goes into this function, and gets processed and encrypted out. Okay, after that we have to input the in length. So what exactly is the use of in length is that we know that each chunk is of 16 bytes. So what is the use of inline? Basically, it is used to handle the edge cases here, because we know that for some kind of during the last of the encryption process, the last chunk not mm, could have contained 16 bytes, but it is also a possibility that it could contain some 10 bytes, 12 bytes, 14 bytes, or something like that kind of storage, and not exactly 16 bytes. So it is very important to tell the system that how many bytes of data is getting entered into the AES mechanism, so it uses that properly to encrypt and decrypt the system perfectly. Because if we are inputting only 12 bytes of data, and the mechanism is running on 16 bytes. So it would take 4 extra bytes of 000, and those zeros would result into some garbage value when we are decrypting the system. So this would create an error into in the AES mechanism and can cause a very big blunder into the system's workflow. Okay, so the third parameter of the function is the pointer function out. Okay, so after the encryption process is completed, the pointer function out is just a buffer created in the dynamic memory, and out is the pointer pointing to it. Out is the pointer pointing to it, and it is very and it will store the encrypted data, which is going to be received from the encryption process at the AES mechanism mathematics that would happen on the in data present in the in pointer. Okay, so after that, after discussing the parameters, now let us dive into this function. And first we are seeing that there is a variable int outlen, which is initialized as 0. So what exactly is the use of outlen? So whenever we are encrypting something, so it is very important to know that either the encryption process is successfully occurred or not. So it is very important to know that is the inline, the size of the data that is getting entered and the size of the data that is getting stored into the out pointer is equal. So for that we are defining an outlen variable, which would store the length or size of the data getting stored inside the output pointer. Okay, so now after that we are using an inbuilt function inside the if command block, which is evp encrypt update. So what is the function of this encrypt update function? So what this function does is that is basically takes the 16 byte, apply all the mathematics and mechanisms, all the algorithms, all the things which we have studied. This is the basically the main function that handles all the mathematics and operations and contains all the algorithms that handle the AES mechanism. So this function takes the 16 bytes of data and encrypts it and puts it again into the output or the out pointer, which we have mentioned in the parameters. So what are the parameters of this built-in function is that first of all it takes CTX. So it is as we've discussed that it is very important that the cipher context window have every update what exactly is happening during the whole of the encryption process. So CTX should be mentioned in each and every function, so that all the context of the encryption process reaches the CTX window, which can be further used for authentication and proper processing of the AES GSM mechanism. Okay. Next is the out pointer, as we have which we have got from the parameters, which is basically the output memory storage where the encrypted data would be stored. Okay. After that, we are using a pass by reference of outlen. So outlen, this is basically we have initialized the outlen is equal to 0 in starting, and the function returns outlen whenever it returns the encrypted file. So what basically is this, that it takes all these parameters, and at the time of returning, the function either returns the outline or it returns -1. If the process is successful, it returns how much data has been written into the output memory, and if not, it returns -1. Okay. So basically, what happens is that we have passed outline in pass by reference, so that the initial zero value of outline can be changed according to the needs, that what is the output given by this built-in encrypt update function. Okay. So after that, we have given the in pointer and the inlen for knowing how much data is getting inputted into the function. Okay. Then we have assigned return equal to -1 for this return -1 for this function. And if this function fails, if this function fails, it would return -1, and if it's successful, it would return outlen. It would return how much data has been written into the out pointer. So we can know that this much data has been written, and we have to process this much. We have to process this much left blocks into the system. Okay. Similarly, is the update decrypt function. It uses all the similar type of data. And the basic difference is the EVP decrypt update function. It is also a built-in function which is basically the reverse of all the mechanisms, as we have discussed the decryption mathematics and the mechanism earlier. It basically takes all those mathematics from the paper into an coding algorithm and compiles it into a function. Okay, so it also takes all the same parameters: the output pointer, the output length, input pointer, and input length. It also returns output length or minus one as the encryption update function also. Okay, now we'll see that there is a method called set tag in here. So what exactly this function do? So if we see that this function takes a parameter pointer as tag pointer. So what this function is basically used. So set tag function is basically to retrieve the to retrieve a tag from the already encrypted file. Basically, set tag is a function used during the decryption workflow. Whenever we are starting to decrypt a file, it is first of all what we do that before decrypting the file, we first of all extract mode byte, extract initialization vector, extract the key, and extract the tag from the encrypted file. So all these extracted things are stored in one place, and set tag is important and stored inside the tag pointer, which would be further used for authentication of the decryption process. Okay, so what exactly this set tag is do? It uh, takes a buffer heap memory of 16 bytes, and then retrieve the tag from the encrypted file and store it in the tag pointer. Okay, so it uses a built-in function, EVP cipher CTX control, which is a built-in function which has total four parameters. So first of all, it has the parameter CTX, which is the cipher context window during the decryption process, which would contain all this information. As we have discussed, that the mode byte, initialization vector, key, tag, all these things are stored in some place. So cipher context is the place where all these things are stored and further used for the authentication process uh, of the of the decrypted data, so that we can know that the decryption process is successful and there is no tampering, or there is no there is no manipulation with the data in between or during the network propagation of the data. Okay, so so the CTX contains all these information. The EVP control ahead set tag is a command given to this function, which says that to which basically indicates the function to move towards the tag creation or tag extraction process. So moving ahead is basically creation of the tag or retrieving of the tag. Okay, if it would be control behind, so it would be deletion of it would indicate towards the deletion of the tag from the file. Okay, but we are not using it here. So what exactly is the next parameter? Next parameter is the length of the tag which is being retrieved. So we know that in AES 256 GCM, 16 bytes of tag is used. So we here 16 is entered. After that, we are giving the pointer where exactly the tag is going to be stored, which is the tag pointer which we have got from the parameters of the main function. Okay, so what exactly this EVP CTX control function returns is that it returns one if the retrieval process is successful, and -1 if this process is unsuccessful. Okay, So we can see that if it is successful, it would the whole user defined function will return true, else it would return false. Okay. So the next method in this class is get tag function. Okay, this also receives a parameter pointer tag. Okay, so what exactly happens here is that it basically whenever this is the function used during the encryption workflow of the system. This function basically, whenever the tag is created into the ctx window, what happens is that we know that the ctx cipher context window contains all the encrypted data. It contains each round, what the round key is used during the each round in the AES mechanism, and how all the rounds are carried off, and what is the encrypted data produced from them. Okay, so the ctx window uses all of them, and apply the tag formation mechanism, as we have discussed, that how the initialization vector is XORed and concatenated with each round of encrypted data, so that it finally outputs a 16 byte of tag, which could be further used for authentication. So this tag is created inside the ctx context window, and this get tag feature extracts that tag from the context window and stores it inside this tag pointer. So basically, it takes the CTX context window as parameter. The control ahead means tag formation command. It takes what is the length of the tag, which is 16 bytes, and it takes the location where the tag is to be stored, which is the tag pointer. Okay, so basically, it takes the tag from the context window and stores it inside the tag pointer. Okay, so the next method inside the class is the finalize encrypt function. Okay, so after all these encryption have occurred, the last thing is to be done is to manage the last 16 bytes, or some last byte of uh, mm, some last bytes of information, and encrypt them into the ciphertext, and also to create the so basically the tag creation process inside the ctx window is initialized by this finalize encrypt function. Okay, so what exactly this function does is that let us assume that there is basically a file contains of 416 bytes of 416 byte of chunks and one 10 byte of chunk. Okay, so basically it is 74 byte of file which is going into the AES mechanism. So first this class initializes the initializes the encryption. It initializes the context window. It initializes the encryption window. After that, using the update encrypt function, it encrypts all the 16 byte chunks, and output it and stored it into the output file. Okay, so after that, what happens is that the finalize encrypt function is called, and this finalize encrypt function, what it would do, it would firstly encrypt the 10 byte of last chunk that is to be encrypted into a ciphertext. So the encryption of the last chunk of any file, any of any chunk or any big folder is managed is, in the AES GSM mechanism, is managed by this finalize encrypt function. Okay, so what are its parameter? Its parameter is only the output pointer where the output has to be stored. Okay, where the outputted ciphertext has to be stored. Okay, basically it is initialized with the outline variable is equal to 0 to know how much ciphertext has to be outputted. So for authenticity, to check whether correct amount of data is inputted and outputted. So basically, the finalize encrypt function first of all encrypts the last chunk, and then it initializes the tag creation process. Till now, as we have discussed, that the four 16 byte of blocks has been encrypted, and a 10 byte block is encrypted. So basically, the context window has all the context window has all the context. It has what is the mode byte of the function, what is the initialization vector of the function, what is the initialization vector of the encryption process, what exactly is the ciphertext in round 1, in round 2, round 3, and in all the rounds, on all the chunks. Okay, so that all information is stored inside the CTX context window, and then this context, all of this context is used with the initialization vector through multiple mechanism process, which we have discussed in the tag creation process of the mathematics of the AES GSM mechanism. So we have discussed it, and how the tag formation process occurs. So that tag formation process is occurred due to this built-in function EBP encrypt final EX. So what this function takes as parameters is firstly the context window, so that it can know all the outputs, all the ciphertext, all the related information that it needs to create the tag, create the 16 byte tag. After that, it takes the output pointer where the last chunk has to be stored, and the pass by reference of out len, which will tell that what is the size of the last chunk that has been encrypted. Okay, so now this tag creation process is completed inside this CTX window, and the tag is stored inside the CTX context window only. Okay, so basically this EVP encrypt final exe returns one if it is successful. It returns -1 if it is unsuccessful. Okay, so basically our function, which is finalize encrypt, returns the output length, the length which has been written into the out pointer, which is the ciphertext obtained after encryption, if the encryption process is successful, and -1 if the encryption process failed. Okay, so and the tag was created inside the context window. Now this tag created inside the context window is retrieved using the get tag method, which we have talked about earlier. So this get tag method extracts this tag from the context window and stores it inside the tag pointer, which is then written into the output files header. Okay, and similar is the finalize decrypt method of this class. Okay, so basically what it does is that it first of all, its feature is to decrypt the last chunk of the GSM mechanism, and its next step is to check whether the tag extracted using we have extracted the tag from the encrypted file using the set tag mechanism. We have discussed it already. Using the set tag function, we have extracted the tag. So the function of this finalize decrypt function is to check whether the uh, whether the uh, whether the tag created by this encrypted file during the decryption process. So basically, the tag formation process is again repeated on its entirety to create a completely new tag, which is named as tag underscore new inside the AES mechanism internally, and then that tag is compared with the tag which we have extracted from the encrypted file. Okay, so these two tags are compared. If they match, so it is assumed that the authentication and the file is completely original, and there is no tampering in between the file. So it ensures the security and integrity of the AES mechanism. So basically, this helps to know that whether the file is completely secure during the network propagation, and there is no tampering in between the process, and the personal information stored inside the files is not changed. Okay, so this thing about the AES GSM mechanism is a very strong point, and it makes AES GSM mechanism, basically it is the point which makes AES GSM mechanism as the international standard of encryption, and makes it so much popular in nowadays digital era also. Okay, so this finalize decrypt function basically decrypts the last chunk, and checks your authentication tag, and finalizes that whether the file encrypted or decrypted is correct or not. Okay, now, as we have discussed our three classes, which is the SHA-256 class, the XOR class, and the AES crypto class. So now we will move further into our code. And first of all, let's move to our PPT, and let's see. Basically, in our PPT, it is a short overview of the SHA class. We have understood what exactly the SHA class is doing, how it is importing the OpenSSL's algorithms and mechanisms into our C++ project and applying it on our data. Okay. Then we have seen the XOR encryption code. Here is a quick overview of that. We have seen how each byte is XORed with each byte of key. We have used how the iteration of the key is used in it. We have seen how it is symmetric and could contain some flaws. We have also seen what could be the possible logical errors into it. We have seen that what is the structure overview, how the private and the public methods and variables are stored in the file to protect the integrity and the security of the file. Okay, after that we have seen the AES crypto class, how this AES class is importing the logics and the functions from the OpenSSL libraries and applying it on our ExCrypt system, so that our ExCrypt system could process the data and apply those mechanisms and those algorithms on our files and folders. Okay, we have also seen that how this AES GSM mechanism class is showing a secure key generation using the SHA, which it is taking. It is showing how private and public methods methods and applications are used so to protect the key and the cipher context window of the AES GSM mechanism. We have also seen how this chunk-wise data handling is done in the system, how the 16 byte data has is chunked in such a way that it formats the mechanism of the AES GSM. We have seen every line of code, line by line, and we have also seen how the data initialization and processing is done, how the key is derived from the password, how the tag is formed, how the encrypt update block is working, how the CTRX control commands are controlling the tag, get tag, and set tag functions, so that the authentication process runs smoothly. Okay, after all of this, we have seen that how GSM mechanism, the tag which is being formed, is stored into the tag pointer, and how how the finalized encrypt functions are ending the encryption or decryption window, and cleansing the window. We are seeing that how the tag is formed, and how the window closes. We also see that how this class is including a destructor which clean all the variables, all the leaked variables, or all the memories that do not contain any value, or does contain any value also, but are now of no use. Example, if we take the key variable, it is now free. We have used the key to form the tag and encrypt the process. So now the key variable is of no use. So we have properly use the OpenSSL cleanse function to remove that key, and to avoid any integrity or authenticity issues into the function. We have also seen that how the destructor is removing and freeing all the values, variables, and all the context which is present in the cipher context window, and freeing it so that the security of the system is maintained. Okay, now before discussing about our core utility functions, uh, before discussing about our core utility functions, let me just give you a code review of what exactly our main function contains. Because after exactly this is our main function. This is our main function. This is exactly the code which we will be going to see whenever we run our compiled file, and the commands and the cout and cin commands that are written here are exactly the output which we will be seeing. So first of all, let us see the glimpses of what we are going to exactly see when we are going to run the system. Okay, so let us first discuss our int main function. Okay, So this is our main menu. First of all, we have defined two directories. You have seen that these are the functions for creating these directories. These two folders have been created using these two functions. Using these functions in the file system library. This fs is the alias name for the file system library which we have imported, and this fs create directories is the function inside it, which is used to create a folder of the path. Now, the encrypted folder path we have mentioned above here, the encrypted and decrypted folder path we have mentioned above here, and this path is used to create these folders. Okay, in our main function. Okay, so when our main function starts, first of all we make these folders. After that, what happens is that we just show some intro message for the system, which is ExCrypt secure file system. Then we are going to start with our main menu. Okay. Now, why is this while true is used here? Because while true is basically used here because for every point that for every menu, for every follow-up menu which we will come across after this main menu would contain a option to reverse back into the main menu. So for that functionality, this while true is used, so that whenever this is set as true, we will return back to the main function automatically, and if it is returned false, we will exit the main function and the program will be terminated. So this while true loop is used here for this functionality. Okay. So now let's move ahead and see what exactly the main menu is offering. Okay. So the main menu offers basically three types of options, which are encrypting a file, decrypting a file, and exit. Okay. After that, we will enter our choice. Okay. Okay. So after that, we will store this choice into a main choice. If we have not entered any main choice and directly entered without giving any input to the system, the program will be terminated. The message will be printed: invalid choice, program terminated, and the program will be terminated in your terminal. Okay. So basically, this handles the edge case of the user giving an invalid input to the system. Okay. After that, we will clean the memory of the scene function so that there is no buffered memory inside the scene function, which could cause error in the system, and cause some error in the workflow of the system. Okay. After that, if you have obviously chosen the option 3, which is the exit option, your system will be exited. Your system will be exited with the message: existing system, goodbye. Okay. And if you have entered any invalid choice which is other than 1 or 2 or 3, so this if else command will handle that. If by chance you have entered 5 in your main menu, so that would result into this output as invalid choice and program terminated, and your program would be terminated from that point, and you have to again start from the starting by recompiling the file. Okay. Okay. After that we will check that what exactly the user have chosen. So we will store this choice in a variable which is encrypt. Okay. So we are taking a bool variable is encrypt. So if the main choice is equal to 1, main choice is equal to 1, which means the user have inputted that he has to encrypt the file. So if he has chosen to encrypt the file, so this is encrypt variable would contain true, and if he has chosen to decrypt the file, so it would contain false, and every other case is already been handled above. Okay. So after the encryption and decryption choice has been stored, so our next menu will appear, which would be for choosing the methods and encryption method which we want to apply. Basically, we know that our system is using two encryption decryption mechanism, which is the XOR mechanism and AE256 GCM mechanism. So we will choose the encryption method from here. We will store it in a variable mode choice. If the users enter any invalid choice or directly enter directly enters without giving any input, so your program would be terminated with this message. And then this cn.ignore is used to remove any buffer in the scene. Then also this part is included into the system, because if we have entered any other values from one other than 1 and 2, so this function can handle all of that, all of those cases. For example, if you have entered 3, so basically this output would be printed invalid choice, and the program would be terminated from that point. Okay, so all the edge cases and all the possible security vulnerabilities which could be in the system, all the possible changes that all the possible flaws that a user can input, all the possible flaws that the system internally could face, are handled properly into the system. Okay, so after that we can see that we are make another variable use AES. Okay, so if the mode choice is equal to do, which is the AES mechanism, if the mode choice is equal to do, so this use AES function, use AES variable would contain true, and if we are choosing XOR mechanism, so it will contain false. Rest all the other cases are handled above. Okay, after this, we will store the infile and outfile string. We have defined the variable infile and outfile. So these variables would store the infile and outfile path. Basically, the input file which contains all the plain text or ciphertext according to the encryption or decryption workflow we are, and output file which is the ciphered file or the decrypted file according to your decryption workflow. Okay, so this is the file path. And if we have chosen is encrypt, so it is checking if you have successfully chosen is encrypt. So if is encrypt is true, that means we want to encrypt the system. This command block checks that if we want to choose encryption system or decryption system. Okay, so what happens is that encryption asks full, we have seen this comment is added here, so that the encryption full path is handled. So basically the system is formatted so that any norm like we have seen that in this test.txt file, this is stored inside the cpp project underscore new folder. So all the plain text files or plain image files or plain video files that are entered into this system, that are entered into the folder, into this folder cpp project underscore new, can be used for encryption and decryption. This system is not yet expanded to a level which could take files from all the computer systems or all the paths. It is still formatted only for this folder. And after the file which is stored inside this main folder, in this main folder gets encrypted, so that files get stored inside the encrypted underscore file folder. As you can see that this test.enc file is stored inside this encrypted underscore files folder. Okay, and this and during the decryption workflow, all the encrypted files are always pull off from this encrypted underscore files folder also only. You cannot bring any external encrypted file into the main function, into the main folder, and then try to decrypt it. It would not allow it. It is only formatted in a way such that it pulls the encrypted files only from the encrypted underscore file folder. Okay, and then stores the decrypted file produced into the decrypted underscore file folder. Okay, so this code block ensure this thing. Okay, so what happens is that if we have chosen the encryption workflow, so then we will first input the file path. This getLine function would input the file path into int underscore file function. Then it would check the edge case that if this file exists, so the workflow will continue. And if it does not exist, if you have entered any wrong name, wrong extension, or any wrong path of the file, so that thing would violate the system workflow of the function, and it would create a error in the function. So this error is completely handled in the system if this we are using the file system libraries exist function to check whether the file path which we are entering is there or not. If it is not found, so the error message would be printed, error file does not exist, and the program would be terminated from here. Okay, else if we have chosen the decryption workflow, Else, if we have chosen the decryption workflow, so what would happen? We will enter the file encrypted file name. The encrypted file name which is present inside the encrypted underscore files folder. Okay, we have mentioned here clearly. Enter the encrypted file name from the encrypted underscore files folder. So what will happen in file? We will input the name of the file, and then this infile path would be changed. To what this infile path would be changed? It would be we will concatenate the path of the encrypted folder which we have seen above, what the path of the encrypted folder is given, and plus infile. So basically what happens is that this formats the system in such a way that during decryption workflow, always the file name which you have entered should always be picked up from the encrypted underscore files folder only. The files only present in this folder can be used in the decryption workflow, and any external file cannot be used in this decryption workflow of the ExCrypt system. Okay, and similarly, it uses the exist function to check whether the file exists or not, and returns the error message accordingly. Okay, after that, it asks you for the output file name. You will give the output file name. It would enter it into output underscore file, and it would check that whether this file is able to be formed or not. Okay. So we will, in case of encryption workflow, we will create a output file inside the encrypted underscore files, and in case of the decryption workflow, we will create a output file inside the decrypted underscore files, decrypted underscore files folder. Okay. So if the output underscore file dot empty is another a string, another string variable, another string function which checks whether the file path is correct or not, and then opens the file. That is it. Is it was the file able to completely was the file was able to be created or not? If it is unable to be created, so the program would get terminated and the program would end. Okay. After that, the program demands you to enter your password, which would be stored in a password variable using the function get password. Okay, we will get underscore password is a utility function which we will see what exactly this get password is doing, which is unique from the cin password method, and how it adds an extra layer of physical security, how that physical security essence also comes into the ExCrypt system, and how it is handled. Okay, so after that, another error edge case can be is handled here. If the password entered by the user is empty, so it would return a password cannot be empty message, and the program would be terminated from there. Okay. Now, as I told you that during the encryption and decryption workflow, the output file would always enter into encrypted or decrypted folders only. So this case is handled here. Okay, so what it says is that the out path is equal if the out path is there. So if we are trying the encryption workflow, the is encrypt contains the value true or false. If the function is in an encryption workflow according to the user's choice, so the output files path would be changes to encrypted folder plus output file, and if it's decryption workflow, so it would be changed into decrypted folder plus output file. So this ensures that the system is formatted such that the in case of encryption workflow, the output files are always entered into the encrypted underscore files folder, and in case of decryption workflow, all the output files are always entered into the decrypted underscore files folder only. Okay. Okay. After that, we will use different. Okay, so after that we will check here that is the encryption and decryption process successful or not. Okay, so here we will check. We have made a bool success variable which checks that if it is encryption process. If it is encryption process, it will call the encrypt underscore file function, which is this function. I can show you that this is the function, that bool encryption underscore file function. What exactly this function is doing? It is taking your password, it is taking the SHA-256 class, it is taking the XOR class, it is taking the AES class, and integrating all of those utility class on all of the other classes to create the workflow of the encryption process. Means it is calling the files, opening the files, creating the output files, creating the temporary files, using the utility functions, using the hashing functions, using the encryption functions. It is creating a workflow of all the things, and creating it in a perfect sequential manner, and also handling the edge cases in all those, in all those function and functioning. And similarly is the decrypt underscore file function, which is handling the complete decryption workflow. It is taking the in path, out path, and the password, and using all the classes which are mentioned above to pull off its process and workflow, so that the decryption process is handled smoothly. It also handles all the edge cases. We will look into it, how it handles and how it makes the workflow of the decryption process. Okay, so so we were on the success variable. So bool success is a variable which would return to true or false if our encryption decryption process is successful. So basically, what happens here is that if is encrypt function is true, so it would call the encrypt underscore file function, which is the encryption workflow function, and would give it the function that is it in file, is it out, it's in file path, it's out file path, whether we are using XOR method as a, or we are using AES method, and your password. All these things are given to this function, and it would use all the classes, all the utility functions, and return you the encrypted file into the out path. Okay. Now, if is encrypt variable is false, so it would call the decrypt underscore file function, which would take your in file, out file, and password. In file basically is the encrypted file, which belongs to the encrypted underscore files folder. Okay, so this file is called, and all the decryption process using all the classes, all the functions, and all the mechanisms is pulled off, and the decrypted data is stored into the out path, which is further stored into decrypted underscore files folder. Okay, it also demands password as one of its parameter. Okay, now, if the success is true, if the success variable is returns true, so it prints success, the operation is successful. And if the success is if the encryption decryption process fails and the success variable contains false value, so the message is printed, operation failed. Okay, after completing all these things, it is very important to handle some edge cases, and for further functionality. Okay, after this whole encryption decryption process is completed, the file is taken and stored into the folders. What happens is that it gives you another menu that do you want to return to the main menu, or do you want to exit? So it gives us two choices. So your choice is stored into the next underscore choice variable. It also handles the case of not entering any choice, so it will directly terminate your program. Cn.ignore to clear the buffer memory. And if you have chosen second option, so your program would be terminated, as the second option is exit, and it would print the message exiting system, goodbye. Okay, else if your system you have entered any other number except of 1 and 2, so this system would not would again give an error message of invalid choice, and program would be terminated from that point. Okay, but there is nothing included for the first option. So basically what is happening here is that we are basically all this code is written inside a while function, so inside a while loop. So if we write here one, so all the except one, all the cases has already been mentioned into this. And if we have entered one, so so the loop would continue, the while loop would continue, and you would again return on the main menu and proceed for further process if you want. Okay, so now we have seen that what exactly the glimpses of the main function are, what exactly our system would represent and show us in the output terminal, what it would show in the terminal when we would run the system. We have also analyzed and seen what are the classes, and how the mathematics of different mechanisms and algorithms are imported into our system. Now we will see the functions involved in the system, and how the mechanics and algorithms imported into the our C++ ExCrypt system is then used to create a workflow which can implement on any file or any folder to pull off the whole encryption decryption system and its workflow. Okay, so now we will look into the glimpses of firstly the utility functions. Okay, so we will see that utility here the core utility functions that are used are mainly four utility functions. First is the make temporary file, second is the save temporary file removal function, third is the get password function, and fourth is the progress bar function. So all these four functions are used for different things. They have different code, and they provide a functionality and a utility in the function which is very important to handle edge cases, or to increase the visibility, or increase the user interaction between the terminal and the user. Okay, so these utility functions contain many different types of function. Now we will understand in depth, line by line code, what exactly these utility functions say. Okay, before understanding line by line what exactly the utility function says, let us now first understand what exactly our system function is what our exactly our system function is happening. For that, we will just run a quick demo of the function, and we will see that how exactly the system is running and how the system's files are working. Okay, so this is our terminal, and we will just run our compiled file. Okay, so first of all, the main menu, as we have seen in the main function, how it appears. Okay, we have chosen that we have to encrypt this encrypt.file. We have a test file present in our folder, which is I'm studying in IIT Roorkee. This is a txt file which we are using for this encryption process. Okay, so we are choosing XOR mechanism to be chosen. Now we will input the file path. So the system is already formatted in such a way that it would take the file path from the cpp project underscore new folder only. It would not take files from the systems downloads or documents. It would take files and folders from this folder only. Okay, so let me just input the file path, which is test.txt. Okay, so now we've entered the test.txt file, and now we are going to enter the output file. So here is the use of utility function, this make.temporary function. Okay, what happens that if I enter the output file name as test1.enc. Okay, so then after the function is demanding password, let me just enter the password as Kushal, and I would just enter. So see, first of all, here we can see use of almost all the utility functions. So first of all, whenever we output a file, whenever we input the output file name. Okay, so directly the output file is not created, because this would miss a very important edge case which we are soon going to discuss what exactly happens. Exactly happens, and the second utility function, which is the save temporary file removal function, is just the follow up of that make temporary function, which is used to remove this temporary file once the output file is ready and the encrypted data is ready. Okay, third, the get password function. This function is used in the enter password functionality. As you can see that I have entered the password as Kushal, but the terminal is showing asterisks in place of Kushal. So this is a very important functionality that is added into the ExCrypt system, so that any person who is speaking into your laptop cannot see your password just by shoulder surfing you, or just by looking into your system, looking into your laptop. Okay, so this prevents a very important vulnerability here. After that, you can see that a progress bar is seen here. In You cannot see the movement of progress bar because here the text test.txt file is very small, and its encryption is so fast that the progress bar directly jumps into the 100% and becomes successful immediately, because it takes a few milliseconds to complete the process, and we are not able to capture that movement of a progress bar. We will use big files in our demo to understand all of this. Okay, so now we have seen that all the four utility functions are extensively used in this. So now we will understand line by line what exactly these utility function do, line by line code. Okay, for that, first we have to understand what this temporary file and this temporary file removal function do, and what exactly how this temporary file is integrated into our workflow. Okay, so it is very important to understand that. So we will be understanding it in this way. Okay, so first of all, we will yes. So we have seen that in this temporary file, we have seen that first of all, it is used to make a temporary file. It is used to make a temporary file. Now, how this temporary file is important? So, a very important thing that is to be noted is that how the workflow works and handles the files input output capabilities. Okay, so first of all, what happens is that we put any input file. Okay, so if we have put any input file here, so what happens is that this input file goes into the system. This input file goes into the system and gets encrypted either by XOR mechanism or by AES mechanism. Okay, either by XOR mechanism or by AES mechanism. So these mechanisms take the input file and change it into an output file. But what if some error occur in between? What if the output file path you have entered is wrong? What if the XOR or AES mechanism faces any error in between? What if the chunk block method fails? What if any particular chunk fails to get encrypted? What if the tag formation fails? And there are many edge cases which we have seen that are handled in the AES and XOR class. What if the password retrieval process fails? What if the hashing process fails? There could be many errors that could occur between this whole input file to the output file process. So what happens is that when you enter the output file, directly the output file is not created. What happens is that this output file creates a temporary file. Okay, so this output file creates a temporary file, and this output file is created as a .tmt file. Okay, now what happens to this .tmt file? In the whole process of encryption and decryption, this .tmt file stores the chunk by chunk data. This chunk by chunk data is written and after all the chunks are written successfully into this tmp file, then this tmp file is renamed as this output file, output file, which renamed as the output file, which further makes our which further maintains the authenticity and integrity of our system. So in this way, we have handled many edge cases and many error causing possibilities. So what happens is that if any error occurs in between during the encryption or decryption system, so what happens? This .tmt file is created. No output file is created directly into the decrypted underscore file system file folder, and this tmp file is created for only a short duration. If the encryption decryption process is successful, so this .tmt file is renamed back into the output file. But if the system fails, so the next utility functionality comes into the action, where which is safe file removal. Okay, so now this safe file removal removes this top safe file removal removes this .tmt file, and save file removal removes this .tmt file, and is then removed from all the folders and all the memories of the system, so that it does not capture garbage memory. It does not cause any leak of error keys or authentication tag or any encrypted ciphertext. So this maintains the integrity and security of the system. Okay, now let us see line by line how exactly this system is pulled off. Okay, so now we will deep dive into the code of the unique make unique temp path function. Okay, so what exactly is the parameter of this function? Exactly what we are expecting. We were expecting it to get the parameter of output path string. So this function gets the output path pass by reference of the output path, because it is very important that it is making changes in the output path itself. It is not creating a copy tmt file of the output path. That a output file is created as well, and we have created a temp file, which is a temporary file, which is a copy of that output file. We have to exactly change that output file only. Okay, so what happens is that we are using here the path data type, which is present in the file system library, and we are allocating this path to an output underscore p variable. Okay, which is then this path is further allocated to a tmp tmp variable. So now this tmp variable have the path of the output file, and this output underscore p has the original file address. Okay, original output file address. Now we will do manipulations on this tmp file path, and we will maintain and in this way we will maintain the integrity of the system. Okay, now very one important thing to be noted is that this function runs once for a chunk. So we know that our chunk size is 64 kilobytes. For each chunk, this function runs once. Okay, it creates one temporary file for each chunk. Okay, so now what happens first is that we will take the tmp path, and we will add a .tmp at the end, .tmp extension at the end of this. So we have seen that as our encrypted file is test1.enc. So this test1.enc is concatenated with .tmp. So the test1.enc whole becomes the name, and .tmp becomes the extension of the file. Okay, now, what happens is that for every subchunk, we have seen that many subchunks are continuously getting processed inside a particular chunk. For AES mechanism, we have seen that a 16-byte chunk is used. For XOR mechanism, we have seen that a 4 kilobyte chunk is used. So these chunks are continuously being used inside our system. These subchunks are continuously used inside our system to make our system easier. So for every chunk, this CMP file would first be created for the output file. Then it would check that the encryption process for that whole chunk is been successful or not. If it is successful, it would write the TMP file data into the original and primary TMP file, temporary file. Okay, so what happens is that this is the primary temporary file path created. Okay, now what happens is that we are initializing int I is equal to 0, and we will be running it inside a loop. Okay, so what happens here is that we will check for each and every chunk. Let us assume that we are running an AES mechanism, and 16-byte chunks are present for 64 kilobytes of a primary chunk. Okay, so what happens is that it would first check that is the tmp file created. Okay, so if the tmp file exists, that means the chunk or the 16-byte memory is present. Okay, so .tmp file the .tmp file has been written with some data, which is the encrypted cipher data for came from came from the encrypted underscore file function, which we are going to discuss later. Okay, so now if this tmp function exists, so what it will do, it will change this path into first of all, the tmt path will be changed into the original output path, and then it would be appended with .tmt plus a string I plus. So first of all, for the first chunk, the file would be output path .tmp1. .tmp0. After that .tmp1, for the next chunk .tmp2, and similarly all the chunks processing would be carried out till all the 64 kilobytes of the primary chunk has been covered. Okay, now if the whole process of this primary chunk data has been successfully done, and the encryption process is successful, encryption or decryption process is successful, so what would happen is that this tmp file would then be written into the main tmp file, which was made during this line. Okay, which was made during this line, which is tmp dot which was formed when we appended the output underscore path with dot tmp only. Okay, so now we will just then return the tmp.string file path, which would contain all the primary all the concatenated chunks data into a temporary file written as, and it would return the path of that temporary file where all the temporary ciphertext is written there. Okay, so in this way, a temporary file with all the data that has been retrieved from the encrypted, or all the ciphertext which has been retrieved from the functions has been written and been checked. Okay, now this is the case when the encryption and decryption process is successful. Now, what happens if there is any error in the encryption decryption process, and we need to remove this temporary file, because we do not want this temporary file to exist in our memory and get into hands of some kind of hacker or exploiter, which can know this ciphertext which is already written into this TMT file, which he can use to exploit your system or your files, exploit your system or files, or know the key or tag authentication tag of your system. Okay, so it is very important for us to delete this file, so that it does not exist in our memory and cannot be exploited. So for this, we have written a safe file removal function. Okay, so what this function does is, exactly, it would take that tmp file. If the function fails, if the encryption or decryption function fails, so it would call so the primary encryption function would call this subfunction, which is safe underscore remove underscore file, and remove the temporary file. Okay, it would remove and delete the temporary file from the path. Okay, so what it would do, it would take a file path, which by reference, it would take the file path of the temporary file, and after that it would take a try and catch value. Because we are handling the errors in this case, it is very important that the safe remove file is itself error handled. Because if any error occurs where the encryption system runs, but there is any error in creation of tmp file or deletion of tmp file, so that error should be handled properly. Okay, because if in case that encryption system works, but the creation or deletion of tmp file system fails, so in that case, a garbage memory would be created, which could be further exploited by the hackers to retrieve your personal information. Okay, so that file needs to already be also be included. So in the try block, we will see that if if this path if our tmp file is not empty, as well as this is the end function, and it needs that both the conditions should be true, then only this command would run. Okay, so first command is that if the first command is not path underscore str.empty, so it would check that whether the temporary file is empty or not. If the temporary file is empty, it is good. Okay, so if the temporary file is empty, it is good, and if it is not, it needs to be removed. Okay, so it checks it. So if the temporary file is not empty, as well as the path of the temporary file exists. Okay, we have used the file system function exist, and so that if the temporary file is not empty and its path exists, so remove this temporary file. Okay, so we have removed the temporary file from our system storage using the file system function remove. Okay, and if this block runs properly, that means That means that a problem has occurred in the encryption decryption process, and since the temporary file contains some information, so that would be removed. But if some error occurs except of the encryption decryption system in any other system, so the block would go into the catch block, and this three dots are to represent any other error except of this error. Any other, it is used to represent this, that any other error except of this error occurs, so ignore it. So we will just ignore it and just continue the system working. So this would maintain the system's integrity. And what happens is that if the encryption system is successfully run, and the TMP file is successfully created, so then also any other system which fails would be managed in separately, which we have already included in the functions or the classes which we have mentioned and discussed above. So any other block, any other error which occurs in the catch block would be ignored. Okay, so that our system runs smoothly and do not causes any user error which the user cannot handle. Okay, so now let us discuss our next utility function, which is the get password function. Okay, so we are seeing that this function is basically used to input our password. Okay, but we know that this is a very basic thing that we can do. We can basically just allot a string a variable password, a string data type to a variable password, and then we can just cin or getline the password. But here, what exactly we have seen that it is very important that a person who can also peek into our laptop and see our password, so that is also a vulnerability we have to manage. So what happens here is that we use different libraries and different systems which we be talking about, which we will be talking about, and how these systems are used so that the password is also not shown or echoed inside your terminal. Okay, and we have seen that we have represented our password as asterisks for every letter that we have entered. Okay, so now let us just go back and just remember one thing, that why we have included these code block. Okay, so this code block is exactly included for this password.get function. Function only. These are the libraries which are required to pull off this password.get functionality in Windows, and these are the libraries which are used to pull off the process in the Linux and Unix. Okay, now, let us see that what exactly this password.input is doing. So first of all, if the system is Windows, we have already seen we have included a libraries for Windows system. So we will be allocating a string data type into a string data type variable which is pass. Okay. After that, we will just give a give a terminal command, enter the password, and we have flushed this command because it is very important that this command is represented immediately after the making of the variable, because the flush function ensures that the output is pushed into the terminal, whether other functions or other iteration or loop or any other functionality is working in the code or not. Because if we directly see out this enter password, it could happen that at the time of password input, any other functionality of the system is working, which could intrude this enter password command, and it would be entered after some time, which is irrelevant for our system. So it is very important that it is entered immediately after the system asks the output file from the user. Okay, we have seen it in the small demo that we have seen, so that how the main menu and the utility functions are integrated during the users input functionalities. Okay, so now what happens is that we have made a variable character ch, and we will be iterating in such a way that every ch present inside the password string is represented as asterisk. Okay, so now, while true, whenever till the ch is contains any value and is not empty, this loop will run. Okay, now ch is underscore get ch. So what exactly is this? This is the functionality of the conio.h library which we have included above for the Windows. And this library, what exactly this library does? This library pulls the first characters ASCII value, pull the first characters ASCII value or the character itself and stores it inside the ch. So if I have entered the password Kushal, so in the first iteration of the loop, the ch would first retrieve k from the terminal. So underscore get ch is used to retrieve a single byte value from the terminal. Okay. So now some edge cases are also handled here. If the value is a new line function or any tab function, we have included it. If it is a new line function or any tab function, so break the loop. So break the loop because we have seen that we cannot directly enter and leave the password empty. We have already inputted that inside our main function, and we have given a proper error message for that in the main function. Okay. So we cannot enter the new line function or the tab function. We cannot okay, new line. Or if we have pressed like let us assume this slash b stands for the backspace key which we press on our keyboard. So this backspace key in the in the ASCII code or in the carriage return which we talk about in the coding terms is slash b, slash n for new line, and slash n are for new line in Windows. Okay, so slash b is slash b represents backspace key in inside the code. Okay. So like if we have like else if we have typed backspace, so what would happen? It would delete one of the one of the values of ch from the password string, so that so that the proper functionality works. Like let us assume that if I have entered Kushal, if I am entering the password as Kushal and I am entering it at I have entered KA instead of KU. So after entering KA, I will press the backspace and then enter U. So what would happen in this else if block if the CH backspace, which is after A I fragged pressed backspace, so what would happen? It would first check that if the password is empty. So we cannot press the backspace when the password is completely empty. So what we are erasing and what we are trying to delete from the backspace, so it does not handle that situation. So if the password is not empty, it would go into this block and it would it would pop the last character stored inside the pass variable, which is a. In our case, we have entered ka and we have pressed the backspace, so it would pop the a character from the password. So what would happen here is that a character would be removed, and we would just remove the asterisk which has also been we will remove the asterisk also that has been added due to a. Okay. So after this backspace functionality is also added into the password get function. After that we will handle the normal letters which are from 32 to 126 of ASCII value. 32 is for space and 126 is for 126 is for exclamation mark. So these from 32 to 126 ASCII characters are managed, and we will just add pass plus ch. So we will just append the password with new character till the iteration works and the ch is getting some value into it. Okay. And we will see out hash we will not see out the ch in this case. We will see out the asterisk in this case. It is very important because the main functionality of this function is to not show what exactly is getting entered into the password. Okay. So this whole functionality is for Windows, and exactly the whole functionality is for Linux and Unix system, and accordingly the commands are used. Okay. After that the password is stored inside the return pass. After that the password is stored inside the pass and it would return the password according and it would be used in further processes. So what would happen here is that this function is basically handling all the edge cases. If we have entered new line, if we have directly entered, if we have any left any empty password, it would handle all those cases. It would handle the backspace case. It would and would handle the all the characters in such a way that those characters do not get echoed into the terminal, and we print asterisk instead of the characters actually being inputted into the inputted into the laptop. Okay, now, for the next utility function, we would be looking into the progress bar utility function. Okay, so what exactly is the progress bar utility function? Whenever the encryption and decryption process is occurring, you have seen that progress bar has occurred, which was showing 100% in our test.txt case, because that file was very small, and the encryption process was very fast in that case. Okay, so that progress bar representation functionality is managed by this under show underscore progress function. Okay, so what exactly it takes? It takes two values. It takes the current value and the total value. What exactly is this current and total? So basically, we are seeing that let us assume that there is a file of 1 GB, and it has been broken into 64 kilobytes according to our chunk value. Okay, so what happens here is that the while processing these chunks, the program would continuously check on which chunk we are, and how much data we have already processed out of the 1 GB. It would count in chunks. Like if you have crossed like let us assume that there are 100 chunks and you have already processed 5 chunks, so the progress bar would show the progress as 5%. Okay, so it would show in the number. So the current would contain the size of the data already been formatted, and the total would contain the size of the total data to be formatted. Okay, so it is also handling the edge case. If total is equal to 0, means it is an empty file, so it would directly return an error, and the progress bar would not be shown. Okay, okay, so after this we will just find the percentage of this. Percentage is current divided by total into 100, which is the basic percentage formula. And after that we will output the progress bar, which we will show. So this is the new line character, and then we have entered a square bracket in which the our progress is shown using the equal to signs. So this for loop is carried on and on till the size of current and total becomes equal, and the percentage becomes 100%. This for loop runs till that it starts from I is equal to 0 till I is equal to 50, because we are taking that 1 equal to in the progress bar is representing 2% of the total size of the function. Okay, so so this is the progress bar function, and we have used directly the flush functionality to output this progress bar immediately after entering the password of uh, password of the file to be encrypted or decrypted, because we do not want that this progress bar is showing after the encryption successful message has been already been printed. So this progress bar has to be printed before it. So flush function is used to directly push this into the terminal. Okay, now we would be looking into the main functions of our system ExCrypt, and we will look into the encryption and decryption function of our system. How these encryption decryption functions are using all the classes, all the utility functions, and integrating all of this with the main function to create a workflow such that it happens everything happens in a smooth functioning, and the workflow do not get disrupted in between due to any error or any edge case, which are properly managed and handled throughout the code, as we are discussing, and in future also we will be discussing all these edge cases. Okay, so now let us deep dive into our first encryption main function, which is encrypt underscore file. It is a bool function. It would just basically return that was the encryption process successful or it was unsuccessful. Okay. So, what are the parameters that this function is taking? First of all, it is taking the path by reference of the in path. It is taking the path of the input file. After that, it is taking a path by reference of the output file path, and then it is taking that is the system using AES mechanism or the XOR mechanism. If the bool use underscore AES is true, so it is using AES mechanism, and if it is false, it is using XOR mechanism. As we have discussed in the main function, that how this use AES function variable is created and how it is calling the encrypt underscore file function. Okay. Now, we can now the fourth parameter of this is obviously the pass by reference of the password, which is going to be hashed using the hash class, and then used, and then the converted key is then used in the encryption mechanisms to derive the encrypted or the ciphertext. Okay. So now, first of all, what we will do, we will open the file. We will open the files using the extreme and extreme functionality of the stream library. Okay, so we are naming the file as in stream in, and we are giving the in the path of the input file, and we are opening it in the binary mode. It is very important to mention that all the files should be uh, opened in binary mode, and all the files that are opened in txt or any other kind on any other mode will not work into the system. Okay, only the binary system would work, because the function at its core and mathematical core is using purely binary functions and not any kind of advanced system that are directly applicable to the numerical mathematics that we study. Okay, so it is very important to open every file in the binary mode. Okay, so if we have open the input file in with a alias name in, so then we will first check the first error case, that if the in is unable to be found, if the input path is unable to be found, or if the in file is the input file is unable to be created, unable to be opened into our system. So this would return a error. It would return an error using the CERR function, which is an error output function of the IOStream library. It would print on your terminal, error cannot open input file. Okay, and we will exit from the encryption function by returning false. Okay, after that we will create a temporary file using the output path, as we have discussed that how particular a particular a particular file, when we have entered the output path, immediately after that a temporary file is created, which is created for the duration till which the encryption or decryption process is completed. If the encryption decryption process is successful, this temporary file is renamed as the final output file, and if it is unsuccessful, this temporary file is deleted. We have already discussed this mechanism of our system, and this this line of code is implementing that. Okay, so we are making a variable temp underscore path, which is making a unique temporary file using the path name out underscore path, which is the output file path. Okay, after that we are opening this temporary file. We are creating this temporary file, and if this temporary file is unable to be formed, or if the output path has any error, or is there, or if any other edge case or any error occurs, so an error would be printed on your terminal. Error cannot create the temporary file. Okay, and our function would be exited by the return false command. Okay, after that, if all the things go well, and our input file is opened properly, and our temporary file is created properly, so we will further move into creating the further variables and systems workflow. Okay, so then we will make an array of initialization vector. As we know that the initialization vector in case of AES mechanism or the XOR mechanism used in our ExCrypt system, used in our ExCrypt system is of 12 bytes. So we have made an array named 4 Roman 4 with 12 variable with the size of 12 unsigned characters, and we have given each and every value as 0. Okay, so we have created an array for the initialization vector. Now we will fill the value inside this initialization vector. So we have already discussed that this initialization vector is created using the rand underscore bytes function inside the OpenSSL rand.h library, which we have discussed earlier. Okay, so we will use the if command to implement that command, and we will check if we are using the AES mechanism, and the rand byte function is returning the output as true. Okay, so basically the rand byte function takes up the parameters as the array, which is going to store the initialization vector and the size of that vector. Okay, so if that vector if that function returns false, so that means that we are using AES mechanism or XOR mechanism. In any case, basically we know that the initialization vector is only present in the AES mechanism. So if any of the two conditions fails, either we have chosen the XOR mechanism, or the case in which the rand byte function fails, that means the initialization vector creation process is failed. So this would return an error message which is failed to generate our initialization vector, that is Roman 4. Okay, so what would happen? We will remove our temporary file as the encryption process fails in between, and so it is very important to remove our temporary file. Okay, so we will remove our temporary file, and the encryption function would be exited using the return false. After that, we will be creating the mode byte. Okay, now we know that the initialization vector is only important for the AES mechanism, but the mode byte is important for both XOR and AES mechanism. So it is important to write whether it is XOR mechanism or AES mechanism. Okay, now we will define a variable mode byte with data type character, and we will check that either it is using AES mechanism or it is using XOR mechanism, and we will store that thing in it. If one stands for one is stored in the one is stored inside the mode byte for AES mechanism, and 0 is stored for XOR mechanism. Okay, so now we will take the output temporary file that we have created. Still, the temporary file has been created. So that temporary file that this mode byte is written into our temporary file. This means the write functions takes two parameters. Basically, firstly it takes the pass by reference or the pointer of the memory to which the to which the information is pointing. That has to be written into our output file, which is here out, and then we have to mention the size of the data to be written into the file, which is exactly 1, because character is a one byte data type, and the mode byte is storing the values 1 or either 0. Okay, after that, the mode byte is written inside the temporary file. What would happen? We will check whether our method is AES or XOR mechanism. If the mechanism is AES, we will also write the initialization vector 4 inside our temporary file. And if the method is XOR mechanism, so we will not write the initialization vector, because initialization vector is only used in the AES mechanism. So further, we will be using our hash class, and we will be creating a object hasher from that hash class. So we know that we have created a hash class which is importing the mechanism and the basic mathematics of how SHA-256 is working, and from the OpenSSL library. And now we have created an object for that class to implement the methods and the variables which are present in that class. Okay, so firstly we will be creating a string that is our hashed underscore password, because we know that the SHA-256 password method, which is present in our hash class, is returning a string type output. So So this thing, it needs to be outputted into a string hash class. Okay. Now, when we see that this we have created a variable hashed underscore pass, and we are using the hasher objects method sha256, and we are entering our password as its parameter. So hashed underscore password would store a 32 byte password into it, and then it would be further processed. So after that, we can see that we have created an array of 32 bytes, which is named as key, which has a data type of unsigned character. So what happens here is that the key, the password, the hash, the password which is of 32 bytes, is now then copied from the string into our array using the copy function of the algorithm library. So what exactly this copy function does? It takes two containers and copy their data from one place to another without leaving any traces in between. So what are the parameters of the copy function? Firstly it takes the source, the beginning pointer of the source container. Then it takes the ending pointer of the source container, and then it takes the beginning pointer of the destination container. So basically we are copying the hashed password, first hashed password end and key dot begin. So we are entering the hashed passwords, complete 32 byte password into our key array. Okay. So we have entered, so we have got our key into an array. Now we will further move into things that would be data into our system. We will create some more variables and some more memory spaces so that our workflow could work properly. Okay. So after this, we have created a vectored with unsigned character, with data type unsigned character as buffer. Okay. Now, what exactly is this? So basically, this is the buffer is the dynamic memory or the pointing vector to the heap memory, which will store our input chunk. Basically, we know that our chunk size is 64 kilobytes. Basically, our chunk size is 64 kilobytes, and every 64 kilobytes of data will get stored into this buffer. And then that processing would occur. So this buffer is the storage place of that 64 kilobytes of data till the data is not completely getting converted into ciphertext or the encryption system failing to return the plain text only. Okay. Now the question is that why this buffer is chunk size plus EVP max block length. What exactly is this EVP max block length? So basically we know that the buffer can also act as a context window. So it would contain, firstly it would be containing 64 kilobytes of data, and this EVP max block length is a constant present in the OpenSSL EVP.h library, which we have discussed earlier. So this constant has a value of 32 bytes, which is used by this buffer to store many different things which could be present into this context of the encryption window. So basically it could be the mode byte, it could be the initialization vector, or any other tag or any other header it needs to be included. So basically this is included so that our vector does not get overflowed and lose any information or causes any disruption in the workflow. So basically it is used to handle the overflow edge case. Okay. After that, we have made a variable total read. This total read variable is will contain the information of the chunk size read during the encryption process. So basically, we know that the this show progress utility function takes two variables, which is current and this total. This total contains the chunk being processed and what is the size of the chunk being processed. Okay, so this total underscore read variable would store that. Initially it is initialized with the value 0, and it would be given values in the further function. Okay. After that, we have also made a variable file underscore size using the file underscore size function of the file system library, which is storing the size of the input file which we are using. Let us assume if we are taking the input file as test.txt, it would store the it would store the size of the input file, and This would be used to further in the progress bar functionality, and also in the authentication tag functionality also, to check whether our function is functioning properly or not. After that, there is a terminal output command here, which is showing that which mechanism we are using for encryption or decryption process. Okay, if we are using AES GSM, it would output that, and if we are using XOR mechanism, it would output XOR. Okay, so basically now what happens is that we have now we will move to the actually importing all those classes, all our XOR and AES GSM class, and use it to create a workflow in which this buffer, the data which is stored inside this buffer, is encrypted and written into another buffer, which is then written into the output temporary file that has been created by us. Okay, and then that temporary file, if the complete process is if the complete process is completed successfully, then that temporary file will be renamed into the output file. Okay, so now we will see this. Okay, so now bool, okay, is a variable which we have created to test the error handling of this try and catch block. Okay, okay, so now we will put our entire workflow in this try and catch block, so that any error which occurs during this workflow can be handled in the catch block. Okay, so now let us look into the our try block and see how exactly the XOR or AES mechanism is implemented, and how those classes are used to bring the workflow that we want. So first of all, there is an if command which checks that if your use underscore AES is false. That means that you have chosen the XOR mechanism, and you are trying to encrypt or decrypt the file using XOR mechanism. So now the XOR class would be used here. So exactly that has only done, and we have created an object for the XOR crypto class, XOR underscore crypto, in which a parameter is initialized, which is key. This key is derived. This key is the 32 byte array which is storing our hashed password. Okay, now we will see how exactly this object is used to pull off the XOR encryption system and its mechanism to be applied on our buffer data. Okay, now we will be now this object is when this object is used inside a while loop. What exactly is this while is iterating on? Basically we will be reading our data from our input file, in the chunks, and at the time, as the chunks of our loop of the chunks that we are reading in our loop becomes less than zero, or the length becomes zero. Basically, when the input file data gets over, so our loop will break, and we will move into the further process. Okay, so now the first command inside the loop is in.read. So what exactly this in.read function is doing? It is basically taking 64 kilobytes, which is our chunk size of data, and storing it into our buffer memory. We have created the buffer vector. We've created a buffer vector, and this buffer dot data we have already seen that the dot data is a function which returns the pointer pointing to that memory. So buffer dot data is the pointer that is pointing to the dynamic heap memory that we have created to store our chunk data. So now basically what this in.read function is doing, it is storing 64 kilobytes of data, first 64 kilobytes of data into our buffer memory. Okay, after that we are initializing a len variable, which what it is doing, it will gcount is a function that is present in our Xstream library, and this function is used in security purpose, like in.gcount. What it does is that it counts how much data has been counted. basically we have mentioned above in dot read that it is going to read 64 kilobytes of data. But what if in the last case and in the edge case, 64 kilobytes of data is not even left inside the input file, and only, let's say, 40 kilobytes of data is left. So basically in this in dot read only, it would read 64 kilobytes, but the buffer dot data would only store 40 kilobytes of data, because only 40 kilobytes of data is left inside the input file. So basically this len function would store how much data has been stored inside the buffer memory, and would tell this to our XOR mechanism, so that it do not cause any error in the XORing process, and do not create any garbage value in the whole mechanism to be followed up. Okay. Now, basically these two lines says that if the count or the input data that has been entered into the buffer memory becomes zero or less than zero, the loop will break. So basically this is the command to end the loop, and it will end at the point when the input file is completely read. Okay. So after this, what we will do, we have created that the total read variable in here in our function. Now the use of this total read function would be there. So what exactly we are doing? We will increase the value of total read after each read and after each read of the chunk size. So basically, we are not appending it with the chunk size. We are adding it with the len. So it will count how much value is being readed at all the time, so that this total read can be used inside the show progress function, which is the utility function, to determine how much progress has been done. Because if let's say there are five chunks of 64 kilobytes and one chunk of 40 kilobytes, so basically if the system has read two chunks of 64 kilobytes, so the total read would contain 128 kilobytes of information, 128 kilobytes of size, whereas the file size, which we have counted as input file size, which we have counted as a file underscore size, of the input path of the input file, which would be totally of 360 bytes. So we would use this in the show progress function to determine how much data has already been read and been interpreted, so that a proper progress bar could be created in this process. Okay. So after that, we have used the show progress function. We have entered the total read as our current read data that has already been read, and we have entered the file size, which is the total size of the input file. Okay. After that we are calling the encrypt underscore decrypt function of the object XOR crypto class. Okay. So what exactly was the encrypt decrypt function of the XOR class? Let's take again the look at it. So basically, the XOR class encrypt decrypt function is basically applying the mechanism of the XORing class, and basically the main mathematics that is involved in the encryption decryption process is being applied in this function. What it demands, it demands the length of the data that is being processed, and it demands the place where the data is present, that is being processed. Okay. So what we are providing it, so this we are putting two parameters, which is buffer dot data, where exactly our 64 kilobytes of chunk has been stored, which has to be converted into the encrypted data, and this buffer dot data is encrypted and then again stored inside this buffer dot data only. So inside the buffer memory, which is which is the vector buffer, this buffer is in this buffer memory, the plain text gets replaced by the ciphertext. Now, uh, we will read this ciphertext in length only, because it is very important to handle the edge case that if we have read 40 kilobytes only, so the XOR mathematics and mechanism should be applied only on 40 kilobytes. If it gets applied on total 64 kilobytes, so this could cause an error in the mechanism and the basic mathematics, and it would disrupt the workflow. Now, what would happen that we have stored the ciphertext inside our buffer memory, so inside our buffer vector. So after that, what we will do that we will write this output. We know that the out is the temporary file which we have opened here, we can see that out is the file that we have opened here. And now this temporary file is written by the data, the cipher data, which is stored inside this buffer memory. So this amount, this size of data inside the buffer data is getting stored inside the temporary file, and getting concatenated again and again in the while loop, till the whole input file is read and encrypted and getting stored inside the temporary file. Now, if this whole process is occurred successfully, so our OK variable, which we have defined here, would return as true. That means that the encryption process was successful, and the complete temporary file has been created successfully, and all the plain text has been converted into the ciphertext. Okay, so we have set the OK variable as true. And similarly in this case, if in the further code we see that if this use underscore AES is true, what block of code would be applied, then the AES mechanism would work. And what would happen is that we will make a object of the AES crypto class as AES underscore crypto, and we will initialize it with a key. Basically, this key is the array that 32-bit array which stored our hashed password. Okay, so first of all, we will call the init underscore encrypt function inside our AES crypto class. This function is basically what it does is that it starts our initialization vector, and it creates a encryption context window which would handle our encryption chunks, 16 byte. We know that the encryption chunk is of 16 bytes, so this encryption window will only handle that thing, because for the initialization of this encrypt process, the encryption window creation is very important. So if the system fails to create this initializing this encryption window, so it would return an error message which would be error AES initialization failed. Okay, so and our OK variable would be turned into false again, because initially it was false and it would be false. This means that the encryption process failed and our function would be exited. Okay. Okay, but if our encryption window gets initialized, what happens is that we will again enter into a while loop and and read read the memory into the buffer data memory. We will read the 64 kilobytes of data from the input file into the buffer vector that we have created. So basically, what happens here is now we have again initialize len variable which counts how much data is being read in every read command to handle any edge cases or any error which could occur in between. And if len less than 0 is equal to 0, break lines are used to exit this while loop. If the input file gets empty or all the data has been already read from the input file, so this loop will break and the further processing would start. Okay, so basically, all the systems in this AES mechanism and XOR mechanism is same. Basically, we are using this total read and adding the length that is being read in each chunk processing into the total read. Then we are calling the show progress function to show. to show the progress bar using the current data read and the total data to be read. Okay. After that we are using the update underscore encrypt function inside the AES crypto class. So basically, what this function is doing, we know that update underscore encrypt function updates a particular chunk of data. Like basically, we know that buffer.data contains 64 kilobytes of data for any normal case, and this data gets further divided into subchunks of 16 bytes for AES mechanism to process it. So basically, this update encrypt function processes it. It breaks down into 16 bytes of chunks, processes it, and converts it into the ciphertext. Okay, so what are the parameters of this function? It takes the input, where exactly is the input data stored. It takes the length of the input data. It takes the output, where the ciphertext created after the whole mechanism is carried out is to be stored. Okay, so we have basically assigned all of this into an out underscore len variable. We can see in the AES class that this update encrypt function is returning an outline for a successful encryption process. It will return the output length of the ciphertext that it has written into the buffer.data memory. Okay, so now this buffer.data contains the ciphertext after all of the mechanism, and this is carried out in 16 bytes again and again till the complete chunk of 64 kilobytes uh, is written into the buffer.data memory. Then this out.write function is used to write this ciphertext into our temporary output file. Okay, after that we know that for the AES mechanism it is very important to handle the edge cases, and for that we have created a finalize underscore encrypt class, which handles the last chunk of the input file that has to be managed. Okay, now, as the last chunk of the input file gets stored inside the buffer.data, this finalize encrypt chunk gets activated. Okay, so what this function exactly does is this function basically firstly encrypts this data and store the output ciphertext again into this buffer vector only, and it returns the final length, that what length exactly it has written into the buffer.data as a final ciphertext. And it further uh, initializes the creation of our authentication tag. It initializes the process of authentication tag, in which it takes the initialization vector, it takes the mode byte, and use all the cipher context window that it has created, which is CTX. It has created to process all the information to create an authentication tag, and that tag is then written into the file again. Okay, so basically, we get the final length. How much data exactly has been written into buffer.data. Okay. Now, if the final length is greater than 0, so we will write that data again into the file, so that our complete plain text is gets converted into the ciphertext. Now, it is very important that our CTX, which is the cipher context window, has the tag, and we have created a get underscore tag function inside the AES crypto class. So what this does, it pulls the tag from the cipher context window and stores it inside a tag. What exactly is tag? Tag is a 16 bytes array which we have created above, and this tag is then appended with the values of the tag by pulling the actual tag created by the AES mechanism using the get underscore tag function. Okay, after that this tag is written into the gets written into the output temporary file, and the OK variable is set as true. That means the complete encryption process has been successfully attempted, and there is no error occurred in the between. Now, what it is important to know that what exactly is the output temporary file template that it has in the XOR or in the AES mechanism. Now let us first talk about the XOR mechanism. So firstly, the temporary file of XOR mechanism firstly has a 1 byte mode byte. Then it contains the cipher context. Basically for 1 byte of mode byte. After that, all the plain text that you have entered into your original text file which has been converted into a ciphertext. It is then appended into the file. And after that, in the XOR mechanism, there is no authentication tag, or there is no initialization vector that is present in our output temporary file. So basically only mode byte and our source data that has been converted into ciphertext is present in the output file. Okay. But for AES mechanism, the process is a bit complicated. First of all, there is a 1 byte mode byte present in the output file, which is followed by a 12 byte of initialization vector, which is appended into this output temporary file, which these both completely forms the header of the file. After that, the source data of which has been ciphered using the AES mechanism is stored inside this temporary file, output temporary file. And this after all of the data cipher data that has been stored into this temporary file, comes the authentication 16-byte authentication tag that has to be stored inside this output file. And we have to keep in mind that the source data that is present inside a AES output file contains only the contains only the source data size as the total size of the file, minus 1 byte of mode byte, minus 12 bytes of initialization vector, and minus 16 bytes of authentication tag. Okay, so that thing is very important for us to understand the decryption process further. Okay. So now let us move further, and we have written all of this AES and XOR mechanism inside the try block. And if any error occurs in between for these process, either it is for any context window creation, either it is for initialization of the encryption window, either it is for finalization, or any error occurs in between, it would be handled in the catch block, and the error output would be echoed in the terminal, which would be error encryption process failed. Okay, and the OK variable would be turned as false. That means that the encryption process has been failed and the encryption system has failed. Okay. Okay. After that, if this does not happen and the encryption system is completed successfully, so we will close our input file and our output file. And Mm, and we know that our OK is a variable which is maintaining that whether our encryption process has been successfully completed or it has failed. So we will handle the edge case here. If the OK variable is false, we will remove the temporary file. That means that the encryption decryption system failed, and there has been some error which have occurred, so that the error output would be displayed into the terminal. But it is very important that the temporary file that creates very many valuable data already has been appended into the temporary file, and it is very important to remove that temporary file to maintain the security and integrity of the system. So we will call the safe remove file function and enter our temporary file path, so that our temporary file is removed, and a message would be printed that our output file with output path this is unable to be created, and the function would return false. That means the complete encryption decryption function, which is the encrypt underscore file, failed. Okay. But if all of these systems works properly and the complete system works properly as a workflow, so what we will do, we will rename the temporary file as the output file path name. We will rename the temporary file and all the data stored in it as the proper output file, and then that output file is stored inside the encrypted underscore files folder, as we have done earlier for the test1.enc. Okay. So we have seen this that it has been renamed and stored inside the folder, and our message would be printed that encryption completed, and our function would return true, which would be then stored inside our success variable in the main function, which would further carry on our workflow for the process. Okay, now let us look into the decryption function of the system. Now, basically, same as the encryption system, the decryption system also takes up few parameters. First of all, a pass by reference of the input path. Here the input path here the input path and the input file is not the plain text file. It is the encrypted file that is already being present in the encrypted underscore files folder. Okay, and the output file is a file that would be created inside the decrypted underscore file folder. Okay, and we will enter a pass by reference for our password, which would be further hacked, and using the authentication tag would be used to maintain the integrity and security of the system. So first of all, we will follow the same process. We will open the input file with the alias name in. If the input file is unable to open, we will present an output for that. After that, we will create a temporary file using the make unique temp path function, and we will use that temporary file. If the temporary file is unable to be opened in the binary mode, or if the output file path is corrupted, output file path is wrong, or any error which you have posed is inputted here. So an error message would be echoed in the terminal that error cannot create temporary output file. Okay, after that the same process would be followed for the we know we have already discussed that what is the structure of the encrypted file whenever the encrypted file is stored inside the encrypted underscore file folder. What exactly how much bytes of data is stored, and after what uh, uh, what variable or what value which value comes. Okay, so basically, we know that we have created a variable mode byte, and we will read only a single byte and store this value. We will only read a single byte from the encrypted file and store this value into the mode byte variable that we have made. So basically, we know that either in the XOR system or in the AES system, both contains the mode byte as a single byte value in the header and the starting of the encrypted file. After that, we have made a array of initialization vector which is 4. Okay, and initialize it with the value 0 with 12 bytes of array size. Okay, now if the mode byte is equal to 1, which means that if the encrypted file is encrypted from the AES mechanism, so we will also read a 12 byte a 12 byte initialization vector which is 4, and store it into our array 4 array 4, and all of this gets stored inside our initialization vector array. Okay, so basically, in case of XOR encrypted file, our pointer is now at the start of the source code, is at the start of the encrypted code. That is the actual value that has been encrypted, and the ciphertext. And in case of AES mechanism, also we have read the mode byte and the initialization vector, and now our pointer is at the start of the cipher code text. Okay, so we will now call the make a hasher object of the hash class. We will hash our password that has been entered by the user, and then store it inside a array of 32 bytes, which is named as key. We will copy the string of the hashed underscore password into our key, and our the array of our key has been successfully created. After this, basically after this the same procedure would be followed. We would create a buffer which would store our chunked encrypted and ciphertext one after another, which would be decrypted, and would successfully create the decrypted file. Okay, we will create a total read variable which would continuously read the current amount of data that has been read by the system, and would be used into our utility show progress utility, which would present the progress bar. And similarly, the file underscore size will be used to check the what is the size of the encrypted file and use it in the progress bar functionality. After that, a terminal output command is written that what mechanism are we using to decrypt our system. If the mode byte is 1, so it is ASGSM system, and if the mode byte is 0, it is XOR system. Okay, basically we in the similar way we have set a okay variable and initialize its value as false. And now we are starting with the basic importing that XOR and AES mechanism to decrypt the source ciphertext. Okay, now in the try block, first of all we will be handling the case of XOR method. That means the mode byte is equal to 0. Okay, so for this, what we will be doing, we will create an we will create a XOR underscore crypto object of the XOR crypto class, initialized with the parameter key, which is our array that contains our hashed password, as we know from the earlier process. Okay, now, while in loop has to be run. This basically ensures that all of the data that has been continuously being read in the form of chunk size is read to the point till the input file is not completely reached to the EUF, which is the end of file error. Okay, so it would maintain all of these things, so that the complete input file is read till the end of file. Okay, now in this loop we will first encounter this in dot read function, which is basically reading 64 kilobytes of chunk size data from the input source ciphertext into the buffer dot data, into the buffer memory that we have created. We have similar to the encryption workflow, have created a length function which is counting how much data have been stored into the buffer memory. We have created a way to exit our loop if the length of the data read in using the read command becomes equal to 0 or less than 0. The loop will break and further processing would start. Okay, after that we have taken total byte and adding the len variable into it, so that it keeps a track of how much data have already been read. And after that we have called the show progress utility function, so that it could show the progress bar of how much file has already been decrypted. After that, for XOR mechanism, we are again calling the encrypt underscore decrypt function, and we are giving this function our buffer memory, which is consisting our ciphertext, and the length of the text which is the buffer is containing. Okay, so this function again returns us the buffer dot data dynamic memory, which now contains the actual decrypted text, the ciphertext that the buffer dot data memory was containing, that got converted into normal readable plain text according to the mechanism designed in the encrypt underscore decrypt function in the export crypto class. Okay, after that we will write this data into the temporary file. We will write len length of data, the data that we have read in that particular chunking process, and take that length of data from the buffer and write it into our temporary file. And if all of this process carry out smoothly, so we will change the value of OK variable into true. That means our decryption process, complete XOR decryption process, has been successfully implemented, and the XOR XOR decryption process was successful. Okay, Now, if our mode byte is 1, is not 0 and it is 1, so our AES crypto class could work, and our AES crypto class object has been made as AES underscore crypto, which is initialized with a parameter key, that is our that is our 32 byte array that contains our hashed password. Similar to the encryption workflow of the AES mechanism. Firstly, we have initialized the decryption window. Firstly, we have initialized the decryption window using the initialization vector, which was generated randomly using the rand underscore byte function in the AES crypto class. After that, we are entering the data size exactly, that I have told you, that the file size is the total size of the file that the encrypted AES file would be having. But it is very important to remove 1 byte of the mode byte. 12 bytes of means the size of the initialization vector, which is 12 in this case, and 16 bytes of authentication tag at the end of the file. So after removing all of this, we will get the exact data size, the exact source data size, which has been entered as the ciphertext into the encrypted file. Okay. Now, if the data underscore size is greater than 0, it would continuously be reading the chunk size, reading the chunk of the data of 64 kilobytes, and breaking it into 16 bytes of 16 byte of sub chunks, and using the read function using the read function to enter this memory into the buffer data. Then then initializing a len variable to count how much data has been entered into the buffer memory. Then these two lines are used to end the loop if the length of the red amount of data becomes 0 or less than 0. Okay, that means that the input file that we are reading has already been become 0, and all the data has been read, all the encrypted ciphertext has already been read. Okay. After that, we will continuously update the total underscore read variable with len, so that it could be used as the current variable of the show underscore progress function, to show the progress bar of the files while we are decrypting the files. Okay. After that, in the similar to the encryption workflow, we will uh, we will create an out underscore len variable, which would return which would be returned by the update underscore decrypt function of the AES crypto class, which would be taking these 64 kilobytes of chunks, and decrypting all of the ciphertext present in them, and again appending those information again into the buffer vector that we have created, and buffer vector which we have created, and the return of this update underscore decrypt is the amount or the size or the length of the data which we have written as decrypted text inside the buffer vector. Okay. After that, what we will do, we will basically write the decrypted data that has been stored into the buffer vector into our temporary file, and we will decrease the data size by the length. So basically, we know that the data size is a perfect data size variable, is the governing condition for the while loop, and it is very important that this loop does not ends into an infinite loop. So after reading len size of data, it is very important to decrease that size of data from the data underscore size variable. Okay. After after decrypting all the chunks of data except the last chunk, this while loop would be exited, and we would uh, uh, we would be moving into the finalize underscore decrypt function. So what exactly we have discussed that this function does, that this function basically firstly decrypts the last chunk of file, last chunk of data which is present in the buffer dot data pointer, and then decrypts it and writes it onto the temporary file. Okay, so one of the functionality of the finalize underscore decrypt function is this. Second functionality is the tag functionality, which we are going to discuss now. Okay, so first of all, we are creating an array of 16 bytes named tag. Then we are reading after all the chunks have been processed. So only the input file. So now the pointer of the encrypted input file for this decryption workflow is on the start of the tag, the 16 byte tag that is at the end of the file. Okay, so now that tag is read. So 16 bytes of tag is read and stored inside the tag array. Okay, after that we will use the set underscore tag function of the AES crypto class to pull that tag from the encrypted file and store it into the tag array, so that that tag could be checked, could be authenticated further, so that it could maintain the security of the system. Okay, after that, after getting the tag into our tag array, what we will do, we will use an if command and check whether the tag is correct or not. So basically what this set tag has done, it has stored the tag from the cipher context window into the tag into the tag array which we have created, and we have also pulled the tag from the encrypted window, from the encrypted file that we have pulled from the encrypted underscore files folder. So what happens here is that the finalize underscore decrypt, the second functionality of the finalize underscore decrypt function is that it would check the authentication tag. It would itself run the complete the complete tag creation process using the password initialization vector and all the decryption workflow that it has gone through using the cipher context window, and then creates a tag which is internally stored inside a variable which is tag underscore new. So then this decryption finalize underscore decrypt would check that the tag array which is storing the tag present inside the encrypted file, and the tag underscore new array which it has created after formulating the encrypted file is same. If they are same, so it means that there is no tampering, there is no manipulation of data or the personal information or the passwords during the network propagation or the propagation of the packets, and the file or the image or the video or any folder is present in its original format, and there is no and this maintains the authenticity and security of the system. Basically this is the functionality of checking of the authentication tag, which makes the AES mechanism very strong and makes it an international standard of how this mechanism is capable of checking whether the file has been tampered or manipulated in between, and check it in such a way that it does not tamper the data that has been decrypted. It only checks a tag that is this tag is comparable to the new tag, and if it is so it would change the OK variable into true, which means the encryption process is successful. And if it is false, so it would throw a runtime error, that is wrong password or corrupted file. That means a complete encryption process is failed. A complete encryption process has failed, and there is some error or tampering in between the network propagation of the data or the file. Okay, so this errors and all the errors that the try block has shown is managed into the catch block, and it would return it would return a runtime error. It would return a runtime error if the if any exception or error occurs in between. Okay, so all the errors and all the edge cases, all the runtime errors, all the file handling errors, or the encryption decryption errors, all are handled into these two functions that are decrypt underscore file and encrypt underscore file. So these two functions are basically the entire defines the entire workflow of our system, and how basically the files are opened, they are chunked, they are encrypted using the mechanisms derived from the classes. They are basically how these mechanisms encrypt those chunked data and write it into a temporary file, and that temporary file is renamed back into a output file. Okay, so this defines our entire workflow system. And further into the code, if we see that we follow the same procedure, we will close our input and output file. If there is any error, so the OK variable would be false, and this would remove our temporary file. This would remove our temporary file, which would maintain the authenticity and integrity of the system, as we have already discussed, and would throw a error output not created. Okay, if the system is completely successful so this decryption system would change our temporary decrypted file into the final output file, which would then be stored into our decrypted underscore files folder. Okay, so this folder, and the message would be printed decryption completed. Okay, and the function would return true. Okay, so basically this wraps up our complete code, the line by line explanation of the code. And now let us move back into the presentation. So we have seen what our exact core utility functions are, what are our core functions, what how these functions are functioning properly to manage the whole workflow, and and inputting their functions and functionality between the systems to further smooth functioning of the workflow. We have also seen how our encryption function, which is one of the main functions of our system, is carrying out the complete system. It basically how it is opening the file input and output file, how it is chunking the files, how it is then converting those chunked pieces into encrypted ciphertext, and then how it is writing those chunks first into a temporary file. And if the system processing is completely true, and the system returns a successful message for the complete encryption process, then that file is renamed into a final encrypted file, and that file gets stored inside the encrypted underscore files folder. So this is the basic overview of the working of the encryption function, as we have discussed in detail. And basically this is the same functioning of the decryption function also, as we have uh, uh, discussed in detail how the decryption workflow is working, basically how it is opening the input output file, how it is chunking it, how it is using the AES initialization vector and tag to check the security and authenticity of the files, and how it is using how it is then appending and writing those chunks into an output file, into an output temporary file, and how that output temporary file is renamed or deleted according to the successful or unsuccessful decryption process. So we have completely seen our line by line code, and how our ExCrypt system is basically working, and what exactly our ExCrypt system is doing. Now it is very important to see how our ExCrypt system is handling the input output file handling security. So basically this is basically explaining the functionality of temporary file. We have already looked in detail how a temporary file is creating during encryption and decryption workflow. The temporary file is created using the utility function. There is also a utility function of save remove file function, which is very important. If any encryption or decryption system fails, so it removes this that temporary file to avoid the leak of any data. and if the encryption or decryption system is successful, that temporary file is automatically gets renamed into the output file, and that output file is added into the respective folders. Okay. After that, what are the different error handlings and the feedbacks included in our ExCrypt system? So basically, you have seen that our system is extensively using messages and handling every other edge cases. Basically, if it's edge case of input file opening, output file opening, temporary files. Either it is of password detection, either it is of any kind of encryption, decryption flaws, or any system mechanism flaws. All these edge cases and error are handled properly into our system, and this avoids any kind of error at during the runtime, so that the user's experience is very smooth while using the ExCrypt system. Okay, so now it's time to test our ExCrypt system. Basically, we have seen each and every line of the code. We have seen what how the workflow of the ExCrypt system is working, how every file is getting managed, how the encryption decryption workflow is managing. We have seen everything, but understanding the things and seeing those things practically are totally different things. So now it's time to take a demo of our ExCrypt system. So now let us move into VS Code and test our ExCrypt system. So basically, I have added some files. First of all, a txt file, which is written with I am studying in IIT Roorkee. Then a video file. Uh, it also consists of a zip folder, and it also consists of a image. We will test our ExCrypt system using all these different file types, and test that with each and every file type how the system is working, and is it giving the proper decrypted output or not. So now let us begin with our demo. So first of all, we will just run our compiled file, which is main.exe. So first of all, we will see what we have to do with the system. So we will first of all want to encrypt the file. After that, it asks what is the encryption mechanism that we want to use. We want to use XOR encryption mechanism. First of all, we are testing with XOR encryption mechanism. Is that mechanism working absolutely fine or not? Okay, so we will enter the input file path. So first of all, let me just do some things, and let me just rename these files so that it is easier for me to enter the file path. We will This is test.txt. Let me just change its name into photo.jpg, and this is folder.7x, which is easier path. Okay, so now first of all, we will take the test.txt file and check it. We will be converting it into test5.enc, which is our output file, which would we get stored into encrypted underscore files folder. Okay, so now we will be entering the password. So I am thinking that the password we will be entering very generic password for this. It would be 12345 6. But we are unable to see this password in our terminal because we have basically applied this functionality into the terminal using the Windows commands of underscore get ch, and we are not echoing basically the characters which the password is storing. We are not echoing it into the terminal, so that any person looking into our laptop screen cannot know what exact password we are entering into the system for encrypting our file. Okay, so now this encryption process is completed. We can see that it is showing a proper progress bar. It is showing it is encrypted using the XOR mechanism, and it is showing that the encryption process was completed. Now it is asking us that whether we have to return to the main file or we have to exit. Before choosing from this menu, let us first look into our encrypted file folder. So basically, we can see that here encrypt file 5.enc file has been created into this folder. Now let us see this file. Uh, Let us see this file. How this file is getting, how this file is having some kind of encrypted data. Okay, so we can see that this file consists of basically a bunch of symbols, bunch of binary text, and different things which are basically impossible to be read or understood. So, in this way, our XOR system is working and converting this TXT file, which was I am studying in IIT Roorkee, into a bunch of random text, bunch of random binary symbols, binary tags or text, which are very difficult to understand and are cryptographically strong. Okay, so now for the menu, we will return back to the main menu, and we will check that is this test5.enc file is getting decrypted or not. So first of all, we will choose the functionality of decrypting a file. We have XORed this test5.enc using the XOR encryption mechanism. So we will again use the XOR encryption mechanism. Name of the encrypted file. So basically the name of the encrypted file is test5.enc. So we will enter it and the output file. We want that this output file should be basically basically outputted as the original file name only. So we will enter it as test.txt only. So this file would be created inside the decrypted underscore file folder. Okay. So now we would enter the password what we have entered, this which is was 123456. Okay, and it is showing that our decryption processes has been completed. So now let us see in our decrypted file folder that it is containing a file which is test.txt. Now let us check. We can see that the test.txt in the decrypted files and folders, and the test.txt in the original folders, which was the original file, and the decrypted file are exactly the same, and there is no tampering in the data. There is they are absolutely same, and the XOR mechanism and the workflow is working completely fine in case of txt file. Now let us test the system with the images. Okay, so now I am thinking of returning to the main menu, and we would just encrypt using XOR mechanism only. Using XOR mechanism only, we will test for the images. So what exactly is the image path? Photo.jpg. Okay, so we will write photo.jpg into the file path, into the input file path, and after that output file path that would be stored inside encrypted underscore file. So I would keep it photo.enc. I would be using the same password 123456 for in this case also, and the encryption mechanism is completed. So now let us see in our encrypted file folder. We can see that it contains a binary file which is photo.enc. Now let us see it what exactly it's contained. So basically you can see that this image is chunked into many pieces, and is converted into basically just a lot of random binary text, which is basically impossible to be read, and is also so strong that it cannot be reversed back or converted back into the original image. Okay, so now let us test that is this encrypted file getting again converted into its original form or not. Okay, so we are returning to the main menu, and we want to decrypt a file. So we will use the XOR mechanism, as we have used the file. We have encrypted the file using XOR mechanism. So what is the file name? It is photo.enc. Okay, this photo.enc. And what is the output file name? The output file name is uh, photo underscore decrypted dot jpg. Okay, dot jpg. So we can see that this output file would be present inside the folder decrypted underscore files. Okay, now the password for the file which we have entered is 123456. So we have entered it, and our decryption process has been completed. So now let's check the folder. We can see that this is the folder. This is the photo decrypted.jpg, and this is was the original photograph. You can see that there is no loss of details. Every detail has been conserved. So the complete information and the complete encryption decryption workflow for the images for the XOR mechanism is working absolutely fine. Okay, so now let us test this workflow with the XOR mechanism workflow with videos. So, okay, so now let us just XORing it, XORing for the videos. Okay, so video dot mp4 and our output is video dot enc. Okay, password is the same 123456. Okay, and our XORing mechanism can be seen as the video is somewhat bigger, so you should have seen a glimpse of the progress bar moving, but the video is also very small, it's only of 7 seconds. So in this case also the XORing mechanism is very fast, as we know that the XOR mechanism is very very fast. So it is very rare to see a slow growth in the progress bar. Okay, but the progress bar ensures that ensures to show that the process is being completely used up and presenting the accurate progress at any particular time of chunking or encrypting that file. Okay, now let us test our encrypted folder, and we have got a video.enc binary file, and let's look into it. Okay, so it is a very very big file because we can see that a video of 7 seconds broken into bits and bytes and then gets converted into the binary text. It is a very big binary file. It contains Okay, it contains many lines of code. It contains almost 13,000 lines of code. So this makes the video file nearly impossible to be interpreted or read by any person. The reading by functionality is very low, but when we talk about the cryptographic strength, so the cryptographic strength of this function is also very strong because it is using SHA 256 for hashing the password, and then using that password or the key generated from that for XORing mechanism to convert this into a 13,000 lines of pure binary codes and symbols, which is nearly impossible to be reversed to bring back the original video. Now we will see how we can decrypt this file and obtain exactly the same video which we have inputted into the system. Okay, so we want to decrypt the file using XOR mechanism. The encrypted file name is video.enc, and the decrypted file name would be video underscore decrypted dot 24. Okay, so the password for this would be 123456, and we can see that our decryption is completed, and we can see exactly that a video underscore decrypted dot mp4 file has been created in our folder, and we can see that each and every detail of the video has been preserved. If we see the original video. Okay, so the original video and the decrypted video are exactly the same, and there is no loss of information in the encryption decryption workflow. So we can confirm that our encryption decryption workflow is working absolutely fine. Now let us move through and check all these text, image, and video files with AES GSM mechanism. Okay, so now we must begin. We will just return back to the main menu. We want to encrypt the file. We will use the AES CSM mechanism, and firstly we will try to encrypt the test.txt file. Okay, the test.txt file is converted into test test 10 dot enc file. Okay, now we are just entering the generic password 123456, and the encryption process has been completed, and we can see that in the encrypted file folder, uh, uh, test10.enc file has been created, which consists of the encrypted file. We can also see that the encrypted file test10.enc and the test5.enc, which was created using the XOR mechanism, are completely different. Basically, they are completely different mechanism, and the output file created between them is completely different. And the AES mechanism encrypted file is much more random, much more complex, and uses a much more higher and complex mathematical algorithms to pull off this system. So now let us try to decrypt this file. Okay, so we want to decrypt the file using the AES-256 GSM mechanism, and we want to decrypt test10.enc file. We will convert it into test10.txt file, which would be sent to the decrypted underscore files folder. Okay, the password is 123. The password is 123456, and the decryption process has been completed, and we can see in the decrypted file that test10.txt file has been created, which consists of exactly the same text that the original test.txt file contains. Okay, so we can confirm that the AES GSM mechanism is working absolutely working fine for the txt files. Now test it. Now let us test it for images. We are going to use AES GSM mechanism. We are going to use photo.jpg and photo1.enc. Okay, and the password is 123456. Okay, so the encryption process has been completed, and we can see that photo1.enc file has been created inside the encrypted file folder, and this is the whole encrypted data which it is giving. Okay, so this is the encrypted version of that photo.enc using the AES GSM mechanism. Now we will try to decrypt it at and attain the original image from it. Okay, we are trying with AES GSM. The file name is photo1.enc, and the output file name is photo1.jpg. Okay, so enter the password 123456. Okay, now this decryption process has been completed, and we can see that photo1.jpg is exactly the same as the photo.jpg, the original photo, and there is no loss of details. So we can confirm that for images also the AES encryption decryption workflow is working absolutely fine. Now let us at the last now let us check it for the videos, and we will encrypt the system using ASGSM. We will use video.mp4. Okay, and video1.enc. Okay, the password is that 123456, and the encryption process has been completed. We can see that there is a video1.enc file made in the encrypted underscore files folder. So it contains a large amount of binary symbols, almost 13,500 lines of binary symbols and encrypted ciphertext. So now let us check that is this encrypted file getting converted back into the original video or not. So we want to decrypt the file using AES GSM mechanism. The file name is video1.enc, and its output name is video1.mp4. Okay, one important thing is that the extensions and the path and the extensions are very important in this case. So it is very important to use proper extensions, else the file will be corrupted, and different errors would be occurred into the system. As we have discussed, there are many error messages set across the system source code, which could manage the error handling at different parts of the system. Okay, so the password is 123456, and the system is has been decrypted successfully. Okay, so now we will check video1.mp4. Okay, so we can see that this video is exactly same as the original video. This is the original video, and we can see that there is no loss of information in this video. So we can confirm that the AES GSM mechanism is working absolutely fine for any text file, any zip file, any image file, any video, or any other kind of file that could be converted into a binary file and could be put into the system. So after this demo, we will move forward into our systems discussion, and now we will discuss what could be the possible future advancement and future security enhancements into the system, which can make this system a lot more stronger and a lot more resistant to any kind of attack when this system is launched to the actual internet traffic and in front of the real hackers or exploiters on the internet. So basically, before discussing this, we need to discuss some of the flaws which are in this system. So basically, a very big flaw in the system is that the encryption techniques which are used in the system are XOR and AES system. XOR is basically a weaker encryption technique, so we will not discuss that. We will basically focus on AES 256 GCM mechanism, which is our stronger part in the system. So basically, what is the problem with AES 256 GCM system is that it is a symmetric encryption technique. So it is important that in the symmetric encryption technique that as we have seen that the tag, the authentic initialization vector, and and the parts of keys are stored inside the encrypted file, which are then and then further retrieved from the encrypted file to carry on the ES256 decryption workflow. So if there is any expert hacker, so he can extract these information from the system. He can get the mode byte, he can get the initialization vector and get the authentication tag, and use all the three to create a password or generate the key of the system, which could be further used for decrypting your personal data, even when this file is encrypted using the AES 256 GCM method. So this is a very big flaw, that it is a symmetric technique. So it causes a very big issue of transfer of this file and the transfer of the key over the network, that the key can also be exploited and uh, could be stealed into the from the choke points or the nodes of the network, and could be exploited and could be used to exploit your personal information. Okay, so instead of this, the system could also integrate asymmetric techniques. The strongest asymmetric techniques which exist nowadays is the RSA 256. RSA 256 is an is a asymmetric encryption technique, which basically uses a private key and a public key. So what happens is here is that a person encrypts the file using the private key, and the data of that private key is then converted into a special public key that only the destination person have access to. This public key is then used by the destination node or the destination person to use to decrypt the system and access the personal information. Basically, the mathematics and mechanisms of RSA 256 are as strong as AES 256 mechanism, but a very strong point is that it is asymmetric encryption type, and this makes the system a lot more secured and enhanced. Okay, also very important future advancement uh, future advancement that could be done comes from the flaws of hashing techniques present in our ExCrypt system. Basically, SHA 256 is a deterministic and predefined technique whose mechanisms and code are present in open source libraries, which could be easily exploited by the hackers or real exploiters, which could easily generate the key from your password. Okay, so basically what happens is that meaning that the SHA 256 is very deterministic in nature, which means that if I have entered a password 123456, the password 123456 will always generate the same key, whether it is generated in a system A or in system B. Always SHA 256 will produce the same key when the password 123456 is entered. So this poses an error. This poses a very big security flaw, that the hackers and exploiters could find the patterns in these keys and match them with commonly used password by the people. Like 123456 is a very commonly used password, and they can search for patterns in these keys, and guess and make a educated guess of the about the password of other people, which can be further used for exploiting their personal information or identity or their financial assets. So a very important technique that we can include in this SHA-256, and we can enhance the hashing technique is PBKDF2. Okay, what exactly is PBKDF2? PBKDF2 is a technique which which is a layer which acts above the SHA-256, which acts above the 256 SHA-256, and add a extra layer of security in it. So first of all, as we have discussed that how the authentication tag security occurs in the AES-256 GCM mechanism, and how that security tag is used to maintain the security and integrity of the system. Similarly, PBK DF2 is used for hashing. It contains an authentication tag which maintains the integrity of the system and avoids the system from being deterministic, and increase the randomness in the password hashed keys generated. Now, how exactly is the randomness increased in this? So basically, PBKDF2 is based on a technique known as salting. So what exactly is salting? Salting means that when we have like I have entered a password, let's say 123456. So salting is a technique which chooses a random set of characters of few bytes, let's say of 2 bytes, and it would insert this 2 bytes of random characters into our system at any random position. Let's say my 123456 password has been salted and converted into 12AB3456. Okay, so this password is converted into a truly random password, which even the person setting does not know what exactly the salt has been added into the system. So, as the salt is added into the system, this salted password is then is gone into the SHA-256, which creates a very random value each time the password is hashed using the SHA-256. Basically, earlier what was happening, if I have entered 12356 as password, so every time the SHA-256 will give exactly the same key for 123456 password. So but now with the salting technique, as the random salt is getting inserted anywhere between your password, so a truly random keys are generated every time the password 123456 is entered. So this decreases the deterministic nature of the SHA-256. So SHA-256 plus PVK DF2 techniques together acts as a very strong and secure system, which can be further used in future to enhance our ExCrypt system, so that it could become capable enough to act in the real world internet traffic. Also, a very important thing to be noted is that the nowadays real world systems using multiple layers of encryption and hashing techniques. What basically I am saying is that let me give you an example of the Google Cloud Storage database encryption systems that are used by the Google. So what basically happens is that a person enters a data with a password in it. That password is hashed, and the key generated from it is used to encrypt the system using the AES-256 GCM mechanism. Okay, after that, that password goes through the goes further through the RSA 256 encryption mechanism, and which is then converted into another yet very complex ciphertext, and that 32 and that ciphertext which is produced after the RSA 256 mechanism is yet once more time is encrypted using the AES 256 GCM mechanism. So this multi-layer mechanisms create a create a very strong chain of encryptions, which is nearly impossible for any hacker to break using brute force or any strong cryptographic technique that they use. Okay, so this creates our if we integrate these techniques into our ExCrypt system, it could become very strong and could be possibly used in future to handle the actual internet traffic. Okay, so how this system we have discussed how this system can be converted into a real world encryption decryption techniques, encryption decryption system which are used by the which are nowadays used by the companies, large MNCs, for protecting their data, for protecting their databases, for protecting their financial assets, the entire financial market systems, and all the data which is stored inside these systems. Okay, so how we can convert this ExCrypt system into these systems, we have discussed them in such a way that how first of all we will change the hashing techniques, we will add sorting into our password, we will change the symmetric encryption systems to unsymmetric encryption systems, and how we will use multi-layer encryption processing, so that our encryption system ExCrypt becomes very powerful. Okay, now let us move towards the conclusion of our whole ExCrypt project. Is that first of all, what exactly we have learned throughout this video in the ExCrypt system. So first of all, we learned the basics of the encryption. We know what are the applications of the encryption decryption systems nowadays. What where the encryption decryption systems are used. What are some common encryption decryption techniques? What are the techniques used in our ExCrypt system? uh, what is the basic mathematics behind those systems used inside our ExCrypt system. After that, we deep dive into the code. We understand about libraries. We looked into the line by line code. We understand every function, what exact each function is doing, and how it is pulling off the entire workflow of the ExCrypt system. After that, we have seen a quick demo of how this system is working and what is the practical application of this system. Then we have looked into how this system could be enhanced in future, so that it could handle the real world internet traffic, and could be so much cryptographically strong that it could face real hackers and real exploiters on the internet, and could protect other people's information from being exploited. Okay, so in conclusion, I can say that our ExCrypt system is yet in advancements, but it is strong enough to protect any local or any short network packet, or any short local area network that could safeguard the files in a particular area of systems, and could protect the personal information of the people in the network from getting exploited, or making them vulnerable over the network. So thank you for being in this video.